Okay, I have pressed. These 4 seats are for the seminar. Thank you. Okay. Right, guys, let's go.
And Brian is still in shot. And my shot. You are both still in shot. So you have to come forward now. No, round the beat. No, come up towards Mandy, guys. Go towards Mandy. Yeah. Go around it further. You're out of shot. Pete, come there. You're out of shot. So from there and going around that corner, you'll be out of shot. Right. If you go around here, you'll be in shot. You can go around the corner. Yeah.
I don't know.
You're out of shot. So as long as you're out of shot, that's all that matters.
It says it's waiting for you, so that means I have to do something here. Ah!
Wait till we get the green screen on. Right?
Sorry, Rob.
Yeah.
It's not doing it now.
Okay.
I can't find the Creator Studio. You should be on. It says it's waiting for you.
So, where are we?
Hang on. Live streaming.
There you go.
Come on.
There you go.
Live. Okay, we are live. Okay, we're live. Off you go.
Are you and you start the streaming now?
Yep.
Yeah. Okay.
Okay, we should be there.
Okay, so if you wouldn't mind.
I'm going to go and check that we are.
Yeah, that's the spirit. Very exciting. Yeah. Refresh the page.
I'm sure we can get this going.
Last time. It says it's live.
Say something.
Hello.
Go live.
Search your code, which you did. Oh, we are there now.
We're there?
I think so, because it says elapsed time.
Watching one.
1. Okay.
That must be you?
Probably.
Yep, you can stop. Good see.
Let me check that it's on public.
Are we showing up on that screen now? Please.
Oh, okay, it worked perfectly last time.
Don't.
I started the encoder.
So try that. Okay, so we started streaming on that.
It worked perfectly last time. Ah, that's it. That's it. Change that to public. There we go. That's what it is.
All changes here. Are we up now, Mandy? Internal server error. Nice.
We should be going through there. I'll make sure that's the start screen.
Oh. I can see you. Yep.
Oh, you
got it?
You are live.
We are live.
Live. Okay,
Awesome.
thank you. Right, okay. I'll worry about this now. Thank you.
Okay, so we're live.
Oh no, that's playing live.
It Yeah, and the chat's here.
And we're up and running?
Yeah.
Okay, guys, welcome to the first live streaming event. Never done this before, so hopefully we won't have too many more glitches than we've already had. Who knows, we might have at least a million of them. So the whole idea of this event is that we'll make a battery together that's obviously a specific battery. And the reason is we're trying to help people to experiment in battery making and chemistry generally. So we thought we'd have a guided experiment where we do the experiment together. People have kits that will go through the kit in a minute, and they can walk through the kit with us. They have problems, but obviously they can send us questions, and we can watch us actually do it, and we can watch the problems we have, and the difficulties that we have. So that's the idea behind the event. Okay? Obviously the event timetable is going to be about half an hour or so of us chatting with each other. We'll go through a few things, we'll have a look at some stuff. We've got some stuff laid out, so we have some bleach and drink. We'll go through that a little bit, and then we'll go and change our angle and go to the bench and start working through the kit. So the kit that we've sent out is this here. We've all got kit each ready for you, okay? And it contains the bits and pieces that we thought would be quite difficult for people to get hold of. It doesn't have everything. Some of the things you're going to need are things like a simple weight and balance. If you don't have a balance, it doesn't matter, you can just guess the amount, okay? Obviously, the more you guess at something, the more of a variable it's going to be. But to be honest, it's such a robust battery that it doesn't really matter if you guess, it's still going to work. So even if you're guessing, you're going to get some result out of it. If you've got a simple balance, like a Joule's balance, we've got one, we'll show it. That's going to help you, obviously. If you don't have it, it doesn't really matter. You have some kind of measuring devices, again, that's going to help you. Again, if you don't have it, we can guesstimate everything. So we made it as simple as possibly can. But you can do this out of stuff you've got around in the kitchen or in your house, nothing too complicated to get hold of. And all of the more difficult stuff is actually in here. So we open that up, we've got some really interesting pieces. And that's a bit of separator. Now the battery is quite small. You don't need to be making massive batteries to get used to a battery. Much easier to make a small one because you can handle it. When you practice making a few small ones, you can go on to bigger sizes because you're going to be used to making small ones and handling the materials. The other good thing is you don't throw away a fortune because if you make big ones, you make a mistake, you make an expensive mistake. You make a mistake with a little one, it's very cheap, don't worry about it. So these are little batteries, but they've still got plenty of oomph in them. Okay? That's a little bit of specialized separator. It's meant specifically for zinc batteries. Now we're going to make a zinc battery. Rubber gloves, yes you need your rubber gloves. Always need rubber gloves, eh? I mean the materials are harmless, but it's not a good idea to get anything on your hands particularly. So always try to keep things off your hands if you can, but the materials are harmless. And what we've got here is the three main components of the actual battery itself. Now, battery divides into subcomponents. So you have a current collector, which is your basic structure. You have a separator that keeps everything apart and stops it shorting across. And then you have the active material, the bit that is the battery, the bit that's going to react. And these are the active materials that we're going to need. This is called potassium hexacyanoferrate. Nice and water soluble. And here we have a nice little bit of zinc sulfate. Both of these will dissolve in water. When we add those two together, then they'll make an insoluble compound. And that is zinc potassium hexacyanoferrate. And that just drops out as an orange can. Now,
people are saying that the audio is difficult again. Could you try to speak toward it slightly?
So speak toward it and a bit louder?
Yeah, perhaps, because even though we tested last week, people are saying there's a problem.
Okay, sorry guys, we did test it last week, but if there's a bit of a problem, all I'll do is shout. That should help. So, if I'm a bit strained, it's because I'm shouting. So please forgive me guys, I'm going to be shouting at you. Hopefully that helps with the audio. So these are the main components. These two are the actual battery active material. So we're going to be making a zinc hexacyanoferrate by adding these two in solution. Now, we do it as a weak solution because a Prussian blue analog, which is what the hexacyanoferrate is, Prussian blue is iron hexacyanoferrate. It's that blue stuff that they used to use in blueprints. We want to make it small, because if we make it large, it will break. If we make it as tiny, tiny crystals, it will operate really well. So we want to make nanocrystals of this. In order to make nanocrystals, we are big people. We've got big stubby fingers, we can't pick up those little bits and glue them together. So we can control that by using concentration. We just don't give them enough that they can clump together. We make them weak. We make 2 weak solutions, add them together with stirring, we will make nanocrystals. When those nanoparticles form, they'll drop out, we collect them, that's the material we're going to use. So this works really well, but only as a nanoparticle. As a large particle, it will still work, but it will only work for about 5 or 6 cycles. As a nanoparticle, it will work for about 1,000 cycles. So it's that much of a difference. Now, nanomaterials always have a different way of behaving, and it's only to do with the surface area. So if I get a lump of iron and put it out there, it'll rust. It'll just rust nice and slow. If I get nano iron and chuck it into the air, it'll be a flame. So reaction time is much, much quicker when the surface to volume ratio is much higher. Okay, so that's what we need. Problem with this is it's not conductive. So we add a conductive additive. Bit of graphite. So we'll make our nanoparticles, we'll add our graphite, stir them together, and that will be our active material. That's what we're going to use as the cathode. The particles themselves are like little cups. They have holes in them. They can take a metal ion. They can take something into that little hole and hold it. And then they can let that little hole out again. And that's where we get the charge from. This movement of the zinc in and out of that little cup is the charge energy storage mechanism. So it's called a zinc ion battery. The zinc ion insertion battery. We're inserting into those holes. We're all having a shuffle around, guys, because I understand that the audio still isn't that good, so we're moving the audio feed closer to us, so having a shuffle around so you can see. So we've got that, nice bit of material. The other side that we're going to use as the anode is a little bit of zinc. So you've got a couple of bits of zinc, so there's enough to make 2 batteries here. And they'll be the anode materials, a couple of nice clean zinc plates. To support and hold the cathode material, a couple of little bits of graphite. These are only going to be little squares. They're going to be about that size. In order to put that material on, we've got a bit of glue. So that's a bit of binder. That'll glue it onto the cathode, the bit of zinc, bit of graphite we've got there. A bit of filter paper to filter paper those nanoparticles out. It should capture them, okay? Maybe you won't capture all of them, but it'll capture enough that we can use. Now, obviously, we need a weak solution that we add at the speed. The faster we add, the bigger the particles will get. The slower we add, the smaller the particles will be. We're likely to do it quite quickly because we don't have much time, okay? So we'll do it relatively quickly, probably a bit too quickly. So if you want to do it again, you'll have to do it more slowly. But we'll use that to put out one solution into the other and to measure out various amounts, and that will help us form them. And a couple of little bits of test equipment in your tiny little motor. Nothing greater than seeing a battery spinner motor, okay? So that little battery, even though it's such a little area, should spin this motor just fine. So we'll spin the motor, and we've given you an LED. You need to connect the 2 batteries together, so they're in series, and it'll light that LED as well. We may or may not have time to do the LED one, okay? We'll see how it goes. We'll see what time we've got. Obviously, giving you some crocodile clips and a little stir back. So you've got everything you need in there that you might have found at home difficult to get hold of. That's exactly what we're going to be making. Now, it's a specific form of battery. It has 114 watt-hours per kilo as its energy density. It's about as dense as lithium ion. So it's a nice material. It will charge and discharge about 1,000 times if you make the nanomaterial properly. And so it's a nice little battery to be making. And as you know, most of what we do are carbon-based devices. Very interested in carbons. The reason we're interested in carbons is because we like the supercapacitor performance. Now, batteries are very powered and energy dense, lots of energy, but don't give it out very quickly.
Supercapacitors are very power dense. They have lots of power they can deliver very quickly, but they can't take much energy on. Making it with nanoparticles, with a carbon support, actually makes it a bit of a half and half device. All these devices are pretty much made the same way. So what I've got here is a 500 farad green cap supercapacitor, and it's basically a little aluminium tin. And in the aluminium tin, we can take out the central material. Now, it is acetyl nitrile in here, so it will smell a little bit. But hey, if you collapse, we'll just throw water on you, you'll be fine. And we can just nip that open, maybe a little bit, just to open it up a little bit. I can be very brutal with these things. Curtis is moving our food away from our acetyl nitrile. So we have a little metal can, and then we have this roll of paper. We slice that roll open. Can you smell it? Yeah. Nice, isn't it? Maybe. I love the smell of this stuff. Snip off the connection tabs. And this has the same structure as every single device you'll ever meet. It's just rolled up. We'll open that out, and we have about 1.5 meters of carbon-coated aluminium. There's a separator layer. This is coconut fibre, actually, coated onto aluminium. Exactly the same thing, coconut fibre on aluminium, and that makes it a symmetric device, and it's just rolled up. That's right. That's all it is. So when it comes down to these small devices that we're making, we're actually making exactly the same device as a commercial device. Exactly the same. The only difference is it's a bit more obvious, and it's rolled up and stuffed into a can. So we're making exactly the same kind of thing. We're just making it smaller so we can manage it. Any questions?
Now what is your battery going to be in a can as well?
So our finished battery is what's called a bipolar plate design. So this is a straightforward anode and cathode. They're slapped together, they're rolled up. It's just two electrodes. What we do is we make a bipolar plate where we squash the anode and cathode together. So at one plate, it is both the anode and the cathode. There's positive on one side and negative on the other. It means that we can make it half as heavy. There are other advantages we get. When we were looking at that thing, it had a long string of a little aluminium tab sticking off. There's a lot of resistance to get along to that tab and get out. On ours, because it's a bipolar plate, it has micrometers, about 80 micrometers to cross, instead of half a meter.
It's on the very same material.
It is, yeah. Yeah.
On a single plate.
Yes. One side is the anode, the other side is the cathode, of one single piece. Yeah. So the energy only moves 80 micrometers. There's a lot less lost energy. The battery is not only a question of the active material. The active material will give you a certain energy on your battery. But obviously a battery has current collector, separator, can, and electrolyte. There's a lot more material in there. That reduces the energy density, because that material doesn't contribute to the energy per se. It contributes to you getting the energy out, but not to holding the energy. So the more of that material there is, the less dense your finished battery is. If we do a bipolar plate, we can get rid of half of that material. So we can get more out apparently. It's much more energy dense. So we're going to do a bipolar plate arrangement actually. Yeah. Oh, it'll work for me. Yeah, how can you get going? Yeah, no more questions? Like, for instance, what is a Prussian blue analog? Can Prussian blue analogs be used for something else? Are there other Prussian blue analogs available apart from zinc? Aren't they questions you would like to ask? Yes. Awesome!
Request from people who aren't English speaking that you speak a little slower if possible.
Okay, I should try to speak a little slower, I apologise. There are lots of Prussian blue analogues. Prussian blue is the baseline material that everybody understands because that's what was used to make blueprints. But there are lots and lots of different types where you take away the iron from Prussian blue and replace it with another metal ion. We're going to use zinc. We're using zinc because it's cheap and readily available and non-toxic. But you can use cobalt. Cobalt, obviously, is not a particularly nice material, but you can use it. You can use nickel as well. If you use nickel or cobalt, they're actually more energy dense than the zinc. So if you wanted to experiment with this kind of battery, you might want to look at using nickel salts. So if I take that potassium hexacyanoferrate, the orange powder, and I put some nickel chloride in there, I'll form a nickel hexacyanoferrate. Then if I do a cobalt, I'll form a cobalt hexacyanoferrate. Same if I do copper. All of those will actually work better than zinc. We're not doing them because they're more toxic in terms of their materials. If you're a chemist and you know all about your personal protection, by all means, work with those and use those. If you're new to it, you're not too good with your personal protection, don't touch them. So we've chosen one that's really easy to use, but is not the most power dense. Works for you. Yeah.
So, like you are trying to achieve power density, both chemically and physical by construction or adopting bipolar technology builds.
In our finished device, we are concentrating mostly on structure because structure is really what matters in making anything. We all know this. If you take a piece of wood and you structure it well, it'll be a Chippendale table worth tens of thousands of pounds. Equally, if you take a piece of wood and you've never used it before, your table won't be worth very much because you'll make a mess. But structure is where everything matters, and it's only practice. You do it again and again and again until you get good, and then your structures become worth something. So we're concentrating on structure, because structure is the most important thing in battery performance, not the chemistry. This can surprise people. A lot of people think that a strange chemistry is going to be the answer. Let's find a perfect chemistry. It's not true. It's structure that will make a big, big difference to what you do, and that's really important. I mean, the two go hand in hand, okay? So it's not really one or the other. It's not chicken or egg kind of thing. It's the two go hand in hand. But what we tend to do is focus on the chemistry. What we also need to do is focus on the structure. Now, that structure we unroll is a thin plate. Thin plates have lots of advantages. If I do a thin material, they're very power dense. I can get the power out quickly. If I do a thick material, they have a lot of energy, but the power can't come out as quick. So structure will make a big difference. Thank you, Mandy. Sodium hydroxide as the electrolyte. We can use sodium hydroxide as the electrolyte, but one of the things we're doing is using a zinc plate. So if we're using a zinc plate, which has a tendency for dendrite formation in acid and alkaline conditions, we're introducing a limiting factor on the lifetime of the battery. We would expect around about 50, 60 cycles in something like an alkali electrolyte. We're going to use zinc sulfate as the electrolyte because it has availability of zinc ions to donate, but it's a neutral salt. So a neutral salt will suppress zinc dendrite formation. We can do other things to suppress zinc dendrite formation. One of the things we might want to do is to look at the structure of the zinc plate. So if we use a zinc foam, the dendrites will have a tendency to grow inside the reticulations of the foam. If we do something like add a zinc dendrite suppressor, like polyethylene glycol 200, then that will suppress zinc dendrite formation. If we use a hydroxide electrolyte, it will be a big problem. So I wouldn't recommend it. And we're going to use a neutral salt electrolyte. Have you thought of using...
Cymatic.
I'm afraid I don't know what cymatics is. So I don't know. If you could explain to me what cymatics is sometime, we can certainly look at it.
There's something not happening. It's doing that.
Are you having the same thing on the feed?
Yeah.
Is your feed slow down? We're just checking the feed because we think there's something happened to the feed.
I don't know. They're saying YouTube's working and the video has stopped.
No.
Are we
It's
still,
working, right?
you still going on?
Yeah. This is not using this Wi-Fi, it's straight.
Okay, so sorry, it seems to have a slight problem with our Wi-Fi, and it has now picked itself back up again. We were just checking that, just in case you guys have dropped out. So I don't know what cymatics is. If you want to explain cymatics, then so clearly I haven't thought about it. Okay, so where was I? Oh yeah, so we'll be using a neutral salt electrolyte. The reason for that is to suppress dendrite formation, so that we get a much longer life cycle out of the battery.
And also very neutral one, and we can just find it easily.
Yes, yes,
It's very important factor.
yes. Well, zinc sulfate is actually used as a horse feed supplement. I think they put it into horse feed. That's why you zinc. You don't have enough zinc in your diet. You took a bit of zinc sulfate in, and the horses wouldn't have it. No, I didn't. Because obviously I look at electrolytes and selecting the electrolytes to be relatively harmless. So I tried to find things that are just used in other applications in bulk. Things like vitamin supplements, which is what protein chloride is, horse feed, zinc sulfate, other things, polyethylene glycol is antifreeze.
Yeah.
So there's lots of things. So yes, polyethylene glycol addition not only suppresses the dendrite formation, it'll actually lower the temperature that the battery will operate at as well. So it helps with low temperature conditions. So there's lots of reasons we've selected that, and that we're not using no alkali. No alkalis obviously rots things away like okay?
Yeah.
Happy?
Yeah, very
I'm getting excited.
Awesome. Well, in that case, let's switch some coffee and swap over to the bench. Good. So we're going to change camera position. I'm also going to visit.
Oh. Really?
That's good, guys. No, Sandy's getting the point. Don't worry. Sandy will get some matter. I'll not be a second. And it won't be 4 minutes, though, Sandy. It'll be 1 minute. Thank you very much. So I got one. Okay, let's go on. Okay, so for those guys who've got kits, you have a kit. Now's the time to take your kit out because now we're going to be working with the kit. And you've all got a kit each, guys. Okay. They're all identical, obviously. So a battery is made of components. I can't help it.
Complaint after
Okay, so a battery is made of components, and if you think about it as the components, you'll know where to begin. The first and most important component that we're going to be making today is the active material. So if you open your kit and remove the active material components, you'll know what I'm on about. And it is these two. So it is the nice golden powder and this white powder. And they're labelled 1 and 2. And if you check on your list, you'll see it's potassium hexacyanoferrate and zinc sulfate. That's it? Yeah, 1 and 2. So the first thing we're going to be doing is turning those in to our active material. Okay? What do you need to do that? Yeah, easy. Make it really easy on yourselves. It's a really very, very basic step. The first thing you need to do, add it to water. Really, yeah. So I know, remember, we're talking about things that people have never done before. If you've never done it before, you need really basic, helpful instructions. So the first thing we need to do is take some of this and add it to water. So we need a beaker and we need some water. Or a jam jar, or a glass, or a cup. Doesn't matter, just something that will hold your water. So, hold your water, guys! Yeah, that'll do, yeah, awesome. Can we have some water, please, Mandy? Good question. Yes. All you need to do is ask one. How much water do you think you need?
The microphone, please. Every time you turn around, I get nasty comments.
Okay, I shall try to speak at the microphone, guys. But remember, I am going to have to turn around. So if I turn around and say something, I'll turn back around and repeat it. So hopefully you'll get it. So the first thing you need to do is add water. And Ian asked, how much water? My question to him is, how much do you think?
You say the solution has to be very light. I think of something. No, yeah, a little more water and less. Naturally.
Okay, so there's the answer. The solution needs to be very light. So quite a lot of water and very little material. So let's have a wild guess. Because like any experiment, you're guessing first. So let's say 250 milliliters of water and half a gram of material. Is that right? I have no idea. But I make a start with my guess. And that's really important. Make a start. Try something. If it doesn't work, try something else. Not all experiment ends in success. Quite a lot ends in failure. And you learn more from the failure than you do the success. So let's say,
I would appreciate to start from 100 so that it's easier to calculate than half.
Good. That's a good reason. So Fergus says, let's try 100 milliliters. It's much easier to calculate. Good reason at this stage. Now we're going to use deionized water. If you have deionized water, it is better to use it. If you don't have deionized water, you can use tap water. All that will happen is you will introduce impurities into your battery, so your battery will not perform as well. You can use it. Better to use deionized. You can use tap water, but you will get impurities. So yeah, let's measure out 100 milliliters of water.
Everybody?
Why? Unless you want to do something different.
No. I'm happy.
Awesome! Oh, I made a mess. Like working with Forrest Gump.
Can I ask a question? Are we going to add both the same solution, or are we going to create two solutions and add the solutions?
We're going to create two solutions and add the solutions together slowly. Yes, with stirring.
Yeah.
Yes, exactly. Okay, so what I've got here is a jeweler's microbalance. So really simple thing, cost a few pounds. If you manage to get one, awesome. We'll use this when it finally tars itself. There you go. Weighs to 2 points, so it's 0.00. So it's a handy enough device for the kind of level that we want. We'll use that to measure out how much.
Yeah.
Awesome.
How much is this?
Do you know, I don't really know, but a third is finding out. It's about 4 grams.
4 grams, 0.8, let's take it for 1 gram, so 5 strength, so 4 grams.
There's 4 grams in there, so how much do you think? In 100 millilitres? Yeah, half a gram or less. Half a gram sounds like a good number. Let's try half a gram. But really a small amount. Eh? So remember, it is small amounts, guys. We're going to try half a gram. We've tried 100 millilitres, half a gram. Not for any reason, it's just our best guess. If we fail, we can do it again. Of course, I know we won't fail, so that's okay. But if you're doing an experiment and you fail, try again. You're only guessing. Okay, so half a gram, guys. Obviously, you can't measure out exactly half a gram. You need to put a bit of paper in there. You need to press the tar button, and then obviously measure half gram. You put the so to use this, you tear off your bit of paper, put it onto your measuring device, press the tar button, which will take the weight of the paper out, and then you
0.3 gram, so tear.
And then you can use your spatula.
Yeah, you can use the steering stick.
You can use this to scoop out half a gram until your weight is half a gram. Another scoop. A little bit more. So close, so near yet so far. A little bit more. Oh, too much. He's got this, yeah.
It's weird. Okay, now it should be. Not too much.
Oh,
It's there.
it's good enough.
It's there. 152.
Okay, so while the guys measure out half a gram of
Thank you.
of their material added to their 100 millilitres of water, we have 2 materials. We have the potassium hexacyanoferrate
The other one.
and we have the zinc sulfate. These obviously have a molecular weight. Now obviously there's a reaction going on where we take some of the zinc and react it with some of the potassium hexacyanoferrate. And they will react at a specific amount to a specific amount. It's actually 1 mole of one, 1 mole of the other, gives you 1 mole of the zinc hexacyanoferrate. What we should do is find out what the molar weight is, work out how many moles that we've got in half a gram, work out the weight of zinc sulfate for that same molarity. Now I do understand that's quite a lot of calculation, and I was thinking of going through that calculation with you, but I thought it would take quite a long time. So in weight terms, it is more or less the same. Half a gram of potassium hexacyanoferrate is more or less the same number of moles as half a gram of zinc sulfate, more or less. There'll be a bit left over, but that's okay, because it will be a soluble salt, and we're going to filter it. So all we'll get out of that is our reacted zinc hexacyanoferrate. So although we haven't done the molarity calculations and the molar calculations to get the stoichiometry exactly right for the reaction, it doesn't really matter. The reaction would still happen. If we've got too much of one or too much of the other, it'll stay in solution. So when we filter it, we'll get the product we want. It may not be as efficient as we need it to be, but it will still give us the result that we need it to give us. So we're going to do the same weight of potassium hexacyanoferrate to the same weight of zinc sulfate in the same amount of water. So just to help you there, it's a reaction that can't go wrong.
Sorry, in the same amount.
Absolutely, yeah. It can't go wrong. It will go solid when it reacts, and unused reactants will stay in solution, and we'll filter them out. So although we're wasting a little bit, exactly.
Do we stir during the process?
If you add it and stir it, obviously, it will speed up dissolution. You can just swill it in your hands if you like, you can stir it.
You have been.
Yeah,
So start.
chuck it in. This one doesn't matter. Just chuck it into your water. And you obviously have 3 more liters to the other one. You've got 2. You do, yeah. And you need another one. I'll give them that yours. Keep going. It will dissolve. Try your stir.
Right, is there room for major error, say an overspill?
Not really. Sorry? Is there room for major error in overspill? What do you mean by overspill? I mean, for a start, we've given you a gram of each, so you're not really going to make much of a mistake. You're adding it to a lot of water. The solubility product of this stuff's quite high, so that gram will all dissolve in water. Anything you add to the zinc is going to react and form the precipitate. If you add it too quickly, your crystals will be too large. If it's too concentrated, your crystals will be too large. It will still give you a result, but it won't be as good. You'll still be able to use the result, but it won't last quite as long. The more careful you are with something, the better your result is going to be, but you will still get a result. So, no, I think is the answer.
Fine. Something is happening if I am trying to add.
No, don't do that.
Don't do it. Oh.
So, Fergus has made the mistake that we were talking about. You need to make 2 solutions. 1 solution of the hexacyanoferrate and 1 solution of the zinc sulfate. 2 separate solutions of 100 milliliters. So I think
This one is done.
And you can still use it. Okay. So you need 2 separate solutions and 2 beakers. Thank you very much for that. Man. So that's when you're doing things happen.
Is there anything here?
No.
So it's okay on this?
Yep. I mean, if we ask Fergus to check his phone again, we'll see.
Yeah.
As you can see, when you're making this, as you can see, if you do half a gram in 100 milliliters, you've got plenty left over for mistakes. And we're still live, sweetheart.
Oh yeah?
Yeah. Yeah, we're good. So, in a real life situation, anything can happen. Remember, you're making 2 solutions. Both of 100 milliliters, roundabout. 1 of the hexacyanoferrate, and a second solution of the zinc sulfate. You can see that the hexacyanoferrate is a yellow color. It's a yellow-orange, actually. And the zinc sulfate is a clear. So you'll end up after this stage with 2 solutions. Oh, they're very beautiful. Matt, do you mind just grab your solution here? Yeah. That's a very beautiful solution. That's what it should look like. This kind of light orangey yellow color. Very light, orangey yellow. That is your solution of hexacyanoferrate. See if you can get that color properly. Looks like that, nice and clear, orangey yellow in color.
Right, will I get chemical burn if this hits some skin?
No, you won't get chemical burn if this hits some skin. But always wear PPE. You are dealing with chemicals, always wear your protection. But you won't get chemical burn if it hits your skin. No. But if you're not wearing your protection, you're not performing your experiment properly. Always wear your protection.
Is there cyanide in this salt?
Yes.
Why are you using this KHCF solution?
Why am I using this solution? I'm sorry, I don't understand. We went through that in the discussion bit.
Make a joint blade?
Okay, so if you join blade, then we're using Prussian blue analogues, insoluble Prussian blue analogues, and we're doing that to make nanoparticles. To make nanoparticles, we're using solution in solution, and we're using a weak concentration to control crystal size growth. So that's why we're using it.
But mine looks green, not orange.
If yours look green, not orange, you have contamination. You perhaps didn't wash your container out properly, something like that. Or you've used tap water and there's a high fluorine content or a high calcium content, and it's gone green instead of orange. It should still be usable, so we can certainly try and use it. But you have contamination if the color has changed. No, it's that green. Okay, so we've got a bit of a cloudy one because of premature addition, where we have a nice one here. If you don't mind, Ian. That's it. That is lovely. Nice clear solutions, and we're ready to go. Now we need to. Awesome. What we need to do is add one to the other slowly. Remember, the size of the crystal is going to be related to the speed at which you do this. We would normally put it onto a stirrer in the lab, but I appreciate you don't have a stirrer. So all we're going to do is take the zinc sulfate solution, put it into our pipette, take our time, stir it, and add, drop by drop.
Slow down your speaking again, please.
Just add it, drop by drop, while stirring. This will take quite a few minutes, but it is worth taking your time over. If you get a bit bored with this stage and chuck it all in there, we'll still be able to use your solution, but your battery won't last as long. Now, we don't do that in the lab, obviously. What we use is a dropping funnel. Where's the dropping funnel, Mandy? Could you, so Mandy's just going to get a dropping funnel for me so you can see what that's like. We set the rate of drop, we put it on a stirrer, and then we go away and have a cup of tea. Now that's awesome when you're in a lab and you have lab equipment. If you're at home and you don't have lab equipment, but you do have your pipette and you do have time and hopefully you have patience, you can just drop them in there while stirring until you've added all of the zinc sulfate to all of the potassium hexacyanoferrate. Then it will form the salt that we're looking for. This is what a dropping funnel looks like. We put that in the stand, we put our solution in there and turn that, and the drop will come out at a drop rate depending on that being turned. So if you happen to have access to one of those, you'll find this a lot easier. If you don't have access to one of those, then you can just do it with the pipette and stir it by hand. Thank you. Thank you. Okay, guys, you now know your next step. Drop by drop. I'll be about 4.5 minutes. Could somebody do it here? Oh, yeah. Yeah.
Good stuff.
Yeah.
I got it. It's fine.
Not quite sure how quickly I'm supposed to do.
I'm just looking at how much I've got together.
All of them.
Well, it's getting a bit not cloudy. Doesn't look like it's moving down. It's 100 million easily take. 5. I'm not feeling that.
So how much is that?
How many times do you do more than 20?
More than 20? Oh, that's not too bad.
If we've done this, we could go for 4 hours. Cloudy as well now. It's been cloudy for a while. Earlier you could see the drop in the cloud now. Earlier you could see the drop in the cloud.
yeah.
Instead.
We're making
I believe so.
It should go cloudy.
cloudy.
Cloudy is good.
We are on target.
Yep.
Good point. When it starts to go cloudy, then it's working because you're getting a precipitate. I wanted to talk a little bit when somebody asked about, is there cyanide in this? If you think about table salt, that's sodium chloride. If you ask the question, is there chlorine in table salt, the answer is yes. Chlorine was a deadly gas used in the First World War to kill hundreds of thousands of people. Chlorine in table salt is not like chlorine the gas. You can eat as much table salt as your heart can manage. It's not going to hurt you. The cyanide ion in here is not cyanide. Cyanide is a deadly poison, as chlorine is a deadly poison. Cyanide isn't, as chloride isn't. But just because it has that in the name, don't run around thinking, I'm going to die.
It is like Blue Peter. So guys, it's a good time to ask questions now if you have any questions. While the guys are adding their sulfate to their potassium, now's a good time for questions. So I've been asked to do a recap for latecomers. What we're doing is we're using the kit to make a zinc ion insertion battery. To do that, we're using an active material, which is a Prussian blue analog. In this case, zinc hexacyanoferrate. We want to make the zinc hexacyanoferrate as a nanoparticle. We're doing that using concentration control through solution. If we use 2 soluble salts, we add them together slowly in weak solution, and they precipitate out, we can make nanoparticles. So the guys have dissolved some of their salts in 100 milliliters of water, actually half a gram to 100 milliliters. And they're adding one solution to the other solution dropwise with stirring to get this cloudy orange solution. It's cloudy because the particles are forming. The particles will form quickly and be large if you add the solutions too quickly, or if you add them too concentrated. So weak and slow is the way to go. For all those who like mnemonics,
Would it matter which solution was put into which?
no. If it's not cloudy, then you haven't mixed the right solutions. If you mix those two solutions together, they will go cloudy. If it's not cloudy, it may be too weak. If it's not cloudy, it may be acidic, in which case you've got contamination. If any of these conditions is true, wash your equipment properly, remake the solutions and try again. You have material enough to do that. The potassium hexacyanoferrate is a water-soluble salt. Being water-soluble means we can control concentration. When we add it to the zinc sulfate, it forms an insoluble salt, a zinc hexacyanoferrate. So we're using potassium because it's soluble to make zinc because it's insoluble. You can use things other than water. You can use other polar solvents, or anything could be used where the solvents are good enough to dissolve both the zinc and the potassium hexacyanoferrate. If you use a solvent like a deep eutectic solvent, that will dissolve the resultant zinc hexacyanoferrate, so you won't get the precipitation out. So if your solvent can dissolve the two salts, but not the zinc hexacyanoferrate, then it will work just fine. If you increase the temperature, so you hold it at something like over 80 degrees centigrade, it will speed up the reaction condition. Remember, to make a nanoparticle, slow and weak. So you want to go slowly. If you speed up reaction conditions, what you'll do is make larger particles. So it's better to do it at room temperature with weak solutions, adding small amounts and stirring constantly. It can be tiring to do this by hand. If you want to make a lot of this, then you're better off getting yourself a magnetic stirrer and a dropping funnel. Then you can make a lot of this without much effort. When you're making small amounts like this in your kitchen or as a home experiment, you don't want to spend a fortune on equipment, a pipette and a stirrer and patience. We can't use sodium hydroxide as an electrolyte. Well, we could do, but it will adversely affect the zinc plate, forming zinc dendrite and ruining the cycle life of the device. You need to use zinc hexacyanoferrate because it's insoluble. Oh, that looks nice. It looks lovely.
Orange juice.
It looks like orange juice. If we leave it now, it will begin to separate. The particles will begin to drop.
Sediment.
So the active ingredients are not zinc sulfate, and they're not potassium hexacyanoferrate. They're not the active ingredients. The active ingredients is zinc hexacyanoferrate. We have to make the zinc hexacyanoferrate, and we have to make it as nanoparticles. In order to make that as nanoparticles, we use two different solutions in a double displacement reaction to form a precipitate of the active material. The active material is zinc hexacyanoferrate.
So how long should we keep it for sedimentation?
Well, we're going to deal with that in a minute because we have two separation strategies available to us. One is sedimentation, the other is filtration. So I'll talk about that again in a minute. When everybody's finished, we'll talk about those strategies. As soon as you've finished, then we can wait and we'll see it sediment out, which will illustrate the one strategy that is a valuable strategy, that is sedimentation. The rate of sedimentation is clearly equal to the particle size. There's a relationship between the particle size and the rate at which it will sediment out. The bigger the particle size, the faster the sedimentation. So if it sediments out too quickly, chances are you don't have nanoparticles.
Yeah, much bigger.
They're much smaller.
Yeah.
Thank you.
Let us see different combinations.
Yeah, should be interesting. Don't skip big.
I've got that sense of a lot. I feel like I've got all this.
So different batch is going to produce different type of solvents.
Yeah. I'm halfway. I'm trying to change this. So I'm weak. We should have teamed up.
Yeah, I think we should. We might should have teamed up.
Okay, why don't you just use activated charcoal from coconut husks? Activated charcoal from coconut husks is what's used in current commercial supercapacitors. It has a specific energy density associated with it that relates to the surface area of the formed husk. The BET number of activated charcoal from coconut husks is round about 600 to 900. That's actually not very high. We use carbons with BET surface areas beginning at 2,000, going up as far as 3,250. If we have those kind of surface areas, we can get good results. If we use activated charcoal from coconut husks, then we don't get particularly good results. Faster charge and discharge from a battery is related to battery structure. If we make the plates thinner and more of them, we can faster charge and discharge it because everything is that much more accessible. If we make the plates thicker and less of them, then they will charge and discharge more slowly because everything has much further to move. So it's really a structural issue. It's about how you structure them more than anything. Zinc hexacyanoferrate, incidentally, has an energy density of around 114 watt-hours per kilo. If you're using activated charcoal from coconut husk, you can expect an energy density of around about 3 watt-hours a kilo. So there's a very big difference in using a Prussian blue analog than there is in using an activated charcoal. One of the main reasons for this is that the shape of the Prussian blue analog is much, much better in terms of accessible surface area for the insertion of the metal ion. Activated carbon doesn't have a particularly porous shape. These zinc hexacyanoferrate nanocrystals do have a bigger surface area, a lot more accessible points, active points, that we can insert zinc ions into, which is why it's so much better. Now, activated carbon from coconut husks is cheaper. And you make a choice, really. If you want a cheaper device, but you want one that is not as energy dense, go for activated carbon. If you want a slightly more expensive device, but has a lot more energy density, go for something else. And this is a suggestion of what to go for. Some potassium ions will get trapped in the zinc hexacyanoferrate lattice. That's going to be a question of your ability to wash them. Now, we're only going to filter them. We're going to filter them and collect the residue and use that residue directly. We could wash it and filter it again. We can centrifuge it if we want. We could spend a lot of time and money purifying that material, and it will, without a doubt, improve the material quality. But like anything, there's a cost-benefit ratio to everything you do when making batteries. If you spend a lot of time and a lot of money filtering and purifying your result, but only get another watt-hour per kilo out of it, you have to ask yourself, was it worth it? And you must make that decision on everything you do. Is the benefit you get out of it worth the effort you put into it? Look at this. We can see how some people are quicker than others. So at the moment, I've got Matt as number 1 on the patient scale, Ian as number 2, and Fergus just can't wait to finish.
I may finish. I won't have time.
You'll have to stop stirring.
Yeah, that's all right.
Oh yeah, you've speeded up now. You're in competition, eh?
Just slow down. It's not right.
Yes! There's a prize for one who finished last.
Got odds on paper at the moment.
Mine looks more orange and yellow white.
Orange is good. If it looks more orange, that's good. Is it possible to make lithium-ion batteries from scratch? The answer is yes, it is. If you're a chemist with experience, you can make them from scratch. It is not an easy job to do, I warn you, but you can make them from scratch. One thing you can do actually is buy the components. There are places like MTI, for example, or here in the UK we have a company called PiChem, that's Pi-KEM, and they will sell you the components already on current collectors, and you can make up batteries that way. So you could make them completely from scratch if you wished, or you can buy components at various stages of readiness and make your own lithium-ion batteries. So the answer is yes, you can.
How much is he worth?
Ian asked a really good question. How much would you save doing that? Is it worth it? You would save none at all. It would cost you a fortune, and your batteries wouldn't work any better than the ones that you buy off eBay. So no, you need a factory to do the kind of production. Lots of control, very expensive, and you wouldn't really save much, no. Mrs. Stewart's bluing, incidentally, is Prussian blue.
Well, I've been doing it.
Oh no, you've been doing it, man. You are doing it. No, you're a chemist now. No hold bars chemical situation. Okay, so we're kind of joking with you, Matt, but it's exactly right. What you're doing is right. You're taking your time, drop by drop, giving it a stir. It is spot on. Yeah. So as you know, I've got a question here. When will your batteries be commercially available? As you know, we're working on the pilot line right now, and we expect pilot line production to begin in about 4 to 6 weeks. The first batteries will actually be for the Twizy, so we're hoping to get batteries in the Twizy before Christmas. The pilot line is to work out the full commercial version, and then we hope to go into commercial production straight after that. The commercial availability, I would guesstimate at about 6 to 12 months, somewhere around about there. We are thinking about doing a pre-ordering campaign so that we can think about people who would pre-order the batteries. Once it's finished, you can leave it alone. It's all done. You don't need to continue stirring. I know you're using your right hand to stir.
Eventually, I was using my left earlier.
Oh, ambidextrous!
Yeah. I thought I was halfway.
So you can test it.
Yeah.
Yeah. Oh, brilliant.
Yeah.
When, after Christmas.
Mate, I'm hoping before.
Oh, wow.
So I'm saying 4 to 6 weeks to give me time.
Yeah.
Because you never know what comes up. We've got one more piece of equipment to arrive, which is supposed to arrive next week. And I'll be making a battery next week. If I can get that sorted, 2 weeks mucking about to ruin everything, obviously. Yeah, yeah, it's going to happen. You're going to break lots of things, you know. And then make the Twizy batteries and stick them in there. I'm hoping in 4 to 6 weeks we'll have that Twizy running. Right. So we're looking at pricing of them. Now, obviously, we're going to be in a market, so we want to make them competitive. It's very difficult for us to say what the price will be. So although I'm going through the exercise of working out exactly how much they cost to make, so it's not just a matter of the material cost. We have to think about the energy cost and the labor cost, the markup that retailers have got to have, and all that sort of stuff. We're going through that exercise right now to work out what that price will be. Now, obviously, we need to be competitive on the market, so we will be competitive, but we don't know 100% just right now what that price will be.
Is the 3D battery like refurbishment?
Yes.
Yeah.
Yeah. Yeah, the basic design is the blade design. Exactly what we're going to have. Yeah. So it'll look like the blade. So it'll be 2 yellow plates with a big black block in between, looking like a bumblebee. Yeah. Yeah, that's what it looked like.
Would it be like refurbishable back with you, or like
Refurbish themselves.
trying to buy stuff to refurbish?
Yeah, I mean, it's going to be a question of skill level.
Yeah.
You know, I mean, can you make your own dining table? Well, yes, you can.
Yeah.
But all you have to do is go down B&Q and buy some wood. Most people will make a mess out of it because they just don't have the skill. And that's okay because they have skills in other places. So it's not possible to have skill in everything. So yes, you could refurbish them yourself, no worries at all, if you have the skill.
Yeah.
Chances are you don't, so you're better off taking it to a refurbishment area. I mean, I was thinking we would refurbish them for you, or we would have retail agents who would refurbish them at obviously a reduced cost. But the plan is that they are refurbishable, yes. But you may not actually be able to do them yourself because of skill level. Could you add activated carbon powder directly into the solution? Yes, you could, and it would be very interesting, because what you would do, or what you expect to happen, is that the nanoparticles would form on the surface of the carbon. And that would be a very interesting experiment to try. What I would probably do is mix the activated carbon first with the hexacyanoferrate and give it time to adsorb. After it's had time to absorb, say about 8 hours of stirring, something like that, then I would add the zinc sulfate because it's likely then that the nanoparticles would form on the surface of your activated carbon. That is an awesome suggestion and is certainly worth an investigation. All you guys working on this with your kits and with the spare material, I can recommend that as an experiment. That is really clever thinking. So the scooter, if you remember, ran for about a year. After a year, we did an autopsy on the battery to see what had happened on the inside of it. Nothing, as it happens, it was fine. But if you cut something open with a hacksaw, it doesn't go together very well. So the scooter is sitting underneath our stairs. It's going to get a new battery straight after the twizzing. Now the solutions on the benches have different colours. Those different colours are due to particle size. So where some people have had it a bit quickly, it's a bit more orange. When some people have had a little contamination because they made a mistake in the beginning, it's a bit more pale white. So they're to do with speed more than anything. The current density, the energy density of this particular battery is 114 watt-hours per kilo for the active material. So the battery that we make isn't actually based on this. This is a nice battery material for you to experiment with and for you to learn how to make batteries. Some experimentation ideas have already come up, which are awesome ideas. But the battery that we'll make ourselves is in fact an all-carbon device. So we won't be using hexacyanoferrate, we use carbons. So this won't be the battery that we actually make. When you have some stuff sinking to the bottom, that's awesome. They're actually the particles. They're the sedimented particles you're going to be looking for. So it's what you want. They might be a little big, but that's okay, we can still use them. We are looking for things to sink to the bottom. That's what we want. What are the cons to coating 6 packs of A4 paper and stacking them? Wow. So it's kind of difficult to know where to begin to answer with that one because I don't have enough information. I suppose what you mean is painting A4 paper with a carbon ink on both sides, stacking them up to make a battery, which is a valid way of approaching it. Obviously, the paper is going to have a very heavy weight in relation to the active material you put on it. It's going to soak up a lot of electrolyte. So the energy density of the final device is likely to be relatively low. It's about all I can think about. Mostly, it's a good way to go. Give it a go, do the experiment, obviously not with 6 packs of A4 paper. I would suggest half a dozen sheets and let us know how it works out for you. If you want to make an all-carbon, you've got to remember that the techniques that we're showing here are identical to the techniques that you will use on making an all-carbon. At the moment, we're making an active material. Obviously, you don't just grab any carbon, you need to make the carbon. Now, there are lots and lots of videos that I've done on how to make the carbons. Once you've made the carbon, just like we've made the active material, we're going to go through the steps on how to turn that into an actual device, and you would follow the same steps. So the only way this differs from an all-carbon device is the active material. The processing of the active material after will be identical. So even if you follow through here and you don't want to use this as your active material, make your active material, follow the rest of the steps, and you'll make another device. In some cases, an all-carbon device. Deep eutectic solvents are an interesting development that came out of Leicester University for electroplating. Once they found out they were electroplated, they found out they worked really well as electrolytes. And they work really well as electrolytes in the same way that ionic solvents work. They're usually a mixture of a hydrogen bond donor, a metal chloride salt, and sometimes a choline chloride. So if you take choline chloride, urea, and aluminium chloride, you'll form a eutectic. A eutectic is one where the melting point is suppressed. So the melting point of the basic materials will be higher than the melting point of the finished material. Because it's a liquid, it can act as a solvent. There's an awful lot of really good information on this from Leicester University website. So just a quick note, guys. Some folks have made a donation, and really thank you very, very much. All donations obviously are really gratefully received, and we'll use them, as you know, to put together our battery factory. We are very thrifty with our money. All our money goes into making that battery factory. So any help is really well appreciated, and thank you very much for that. So just in case you're wondering, the guys are obviously making very small amounts because it's easy to do. We made this much, which is about 15 kilos. That obviously took a little bit of patience to do, but you can mass produce this stuff. You can make this stuff in large amounts. Obviously, we used a assisted process. We got a bucket and we drilled a small hole in the bucket. Actually, it was a bin. And we let it drip through the bin from one bin to another. So you can handle mass amounts of this really easily. Small amounts like this are meant for tabletop experiments, for you guys to get a handle on what it is you're doing, but it translates into a large-scale production relatively easily. What was the pink stuff? Oh, the pink stuff was a mass amount of zinc hexacyanoferrate. It was a massive amount of zinc hexacyanoferrate that we made by filling up bins and drilling a small hole in the bin and leaving it. So a good question about separation strategies. Don't you need a centrifuge to remove the particles? Well, nanoparticles have a habit of agglomeration. They like to stick together. They like to gather up. So there are a number of strategies for getting those nanoparticles out of there. One is to give them the time to agglomerate. It doesn't really spoil their properties. If they agglomerate, they will sediment. So if we leave those jars now to one side for a couple of days and come back, they will have sedimented at the bottom and still be nanoparticles. They'll have just agglomerated together. Another way is to use vacuum filtration. Now, initially when you begin the filtration, the first few particles will pass through the paper. The next few particles will get trapped in the fibre of the paper, reducing the pore size of the paper until you get entrapment of your nanoparticles. You can then refilter and you'll entrap more nanoparticles and it will come through. And the other one, obviously, is to centrifuge. You can centrifuge them. Okay, what is the cheapest material to use per watt to make any battery, for example, an earth battery? So, whenever you make a battery, then you're making a decision between cost and benefit. The cheaper materials tend not to perform as well. They're cheaper because they're less pure. Less control has been exercised over them, so there's less porosity in the material very often. It makes them cheaper. the cleaner and more accurate your material is, it tends to be more expensive. So the cheaper materials tend to make less dense batteries. So when you're looking at a battery, you have to look at the purpose to which you want to put it. So you're not going to run an electric vehicle from an earth battery. You just can't get enough battery in the vehicle. Equally, you're not going to use lithium-ion batteries if what you want to do is save a lot of money. So it's not really about cheapest per watt. That's not really the issue. The issue is what function do you want it to perform? And then what cost benefit do you have for the performance of that function? Batteries do many, many things. Yay, done! So the all-carbon device we've created is a hybrid. It's part supercapacitor, part battery. And that makes it energy dense and power dense. Okay, the guys have finished. Lined them up so you can see them, and they're looking awesome. So as I say, we have a number of strategies for dealing with these. If we have a look at this one, I'm not sure if you can see it particularly well. At the bottom, we're getting sedimentation already. At the top, it's a lighter color, and it's going in a darker color. If we leave this for a few hours, we'll see banding. We'll see this go very clear. We'll see a band of whitish orange here and a band of orange there. That is separation. So we can leave one just to agglomerate and separate out. The other thing we can do is we can centrifuge it. And we're getting the same thing here. We're getting, can you see this banding? You see that very light color right there, where it's beginning to separate out. And if you look at the bottom here, you can see the orange powder beginning to collect. Right at the bottom, it's just the very bottom layer. Let's see if we can see it by looking there. Yeah, just. You look underneath it, you can just see it. See it slightly oranger? Yeah? This one's going to take forever. Because this was well made. Sorry guys, this was well made. Okay? That'll take forever. So there are a number of options we can do.
We see different.
So what we're going to do, obviously, with this is when we've separated it out, we're going to make an ink out of it, basically. And then we're going to use that ink to paint onto the carbon plates. So that's the plan of what we're going to do with this. Somebody asked a question that says, high-power car alternators. I am sorry, I don't understand that question. Could you actually expand a little bit? Because I don't know what you mean. Okay, so let's have a look at this. What? Apparently somebody has completely separated already. Excellent! Set it to one side. We're about to show you how to get rid of the water on that. Obviously filtration, okay? So we have a bit of filter paper that we've provided for you. It's just the same as a bit of coffee filter paper. So you could use a coffee paper. This is a Whatman paper. I'm not too sure what Whatman it is, but it's a Whatman paper, so it's quite nice. And we're going to make a little funnel out of it. And all you do is fold it in quarter, open it like that, and we have a little filter funnel. And we can filter into that. It's fairly robust. So it holds its shape quite nicely. If we have some kind of funnel, sorry man, would you pass me that funnel just under there, please? It's underneath the bench. Yeah. Thank you.
A small one.
No, it's okay. So this is obviously a kitchen funnel, and if you stick your thing in there, there's a kitchen funnel, it'll work just fine. Don't fill it up past the filter paper, obviously, otherwise it'll be a bit of a mess. Or you can just find a little cup like that, and you can pour it into the cup, and it'll hold its shape just fine. So we're going to use our massive kitchen funnel, which is a bit dirty, so we're obviously going to get contamination, boo-hoo. We use our massive kitchen funnel, and then just pour your liquid into your funnel.
What is the micro size of this?
The Whatman, I'm not 100% sure, I'm afraid. It is a Whatman filter, and I think it's 206, I'm not 100% sure. So as it begins to filter out at first, it will filter out slightly orange. Remember, you have to wait until some of those nanoparticles are trapped in the fibre of the paper to reduce the pore size.
so we can refilter it after it's done that. And all we're going to do is exactly that, guys. You have to, I'm afraid, hold it like that.
Yeah.
I'm afraid. Mandy, do we have a stand?
Yeah.
You need to put a stand on it. Yeah, that'll work well. Stand. Yes, please. That's your. You don't already know exactly like one of these. Mandy has come to the rescue yet again, providing us with a stand. That's okay, mate. You're going to waste some.
Do they have to wait till it separates to filter?
No, you don't have to wait for it to separate in order to filter it. Yeah. Oh, exactly the same thing. I guess we need another stand. And as I say, it will filter through initially with the material in there. It will also take quite a while to filter through. So again, another good time to ask questions, because we have to wait for it to filter. As it filters, we'll see that the filter paper gets covered in an orange material. That orange material is the material we want. I think Andy's sorting you out more stands, right? Yeah. There's one here. I'll give you now. Yeah. There you go. Oh, and there's another one. Brilliant. So you don't need the stands, it just makes it more convenient for you, okay? If you have like a large jug, for instance, or beaker or vase, something where it doesn't touch the bottom. So we have a large and dirty jug right here. Just put it on the jug.
All right, okay. Like that.
There you go. That'll do it just as well as a stand, right? So I've been asked from binder, why carboxymethyl cellulose and styrene butadiene rubber instead of polyvinyl acetate? Polyvinyl acetate is water soluble. And this is a water... No. Carboxymethyl cellulose and styrene butadiene rubber is non-soluble in water once it has dried. What happens is the CMC expands, but doesn't dissolve. Now, the SBR is a rubber. Once that's set, it's insoluble. The PVA swells and begins to solubilize over time. So PVA works quite well if you're doing something where you're expecting 6 cycles or so. Or you're practicing something, or you don't really care, you don't really want a long lifetime. If you want a long lifetime out of it, then you're going to have to use something like CMC SBR. We use CMC SBR because it's really cheap, really easy, and nice to use. You can use PVDF. PVDF is what's currently used in lithium-ion batteries and supercapacitors. But expensive, it's difficult to use, and you have to buy it as a specialized material. So we use them because they're safe, cheap, easy, and work well. So the hexacyanoferrate battery, remember, has an energy density of 114 watt-hours per kilo. So this is an answer to a question. The dual hemp carbon battery, depending on the process and quality of the carbon that you make, will get about 30 or 40 watt-hours a kilo, somewhere around about there. It really depends on how well you make the carbon. So the problem with 3D printing anything, okay, a lot of people suggest 3D printing of batteries and battery components. That's okay if you're going to make 1 or 2. But obviously we want to make thousands upon thousands of these. So 3D printing in those terms is just too slow. You can do it if you're doing 1 and you're happy to spend ages printing it
No problem at all, it'll work just fine. If you want to make 100,000 of them in a week, 3D printing is not the way to go. It's just not fast enough right now. So a lot of people are really interested in 3D printing. It would work just as a one-off, but not in production. Have you seen ceramic battery cut into pieces safely? Fun to try. I haven't seen a ceramic battery being cut into pieces. I certainly haven't seen one where it's been done safely. Fun to try probably depends on your definition of fun. I quite like taking a risk and running very quickly, in which case, yes, it would be fun to try. If you don't like losing your eyebrows, it's probably not, but that would be up to you. I've never tried it. If you want to try it, do a video. I'd be fascinated to see you do it. So graphene filter paper may be charged with some EMP. Okay, so you have to be careful about adding complication to things. The trick is not to add complication, but to attempt to simplify. When you add complication onto something, you're adding expense, and it quickly becomes an issue of whether you're getting the benefit from the expense you're adding. Now, graphene is very expensive. Charging it with an EMP and maintaining a differential charge is quite a difficult task to do. If it gives you a benefit, like a reduction in cost or a higher throughput on production, it's probably worth looking at. But if the device itself is just too expensive, it's probably not worth looking at. It's just one of those things where you have to make a cost decision about the benefit you're getting over the expense and difficulty of the system that you implement. Now, I'm looking at yours, man. As it drips through, it's dripping through quite cleanly.
It is. Oh, that's good.
It is. Fergus, yours is looking kind of cool too. Are you getting kind of an orange coloration on your filter paper?
Yeah.
Yeah, that's very cool.
It's getting denser.
Yeah, should do.
Yeah.
This is, sorry, guys are asking about the filtration process. This is a basic filtration process. It's what you do in your O-level chemistry. It's the bottom of the line, cheapest filtration method possible. It's cheap, it's time consuming, and it doesn't do a particularly good job. It does a good enough job for what we want. Okay, all of these things are decisions about what's good enough for what we want. It is without a question not the best method at all. If you want to do something like remove salts from graphene, you probably want to use something like dialysis. Dialysis obviously is very expensive, but it's an enormously brilliant way of removing salts from a solution. So dialysis would be a way of removing the salts from a graphene solution after you've done a purification step. It's pretty inappropriate for us to try dialysis on a kitchen table. If we can get a decent enough result out of what we're doing, good enough. And that's all we're really interested in. So solid state batteries are a whole interesting range, and somebody's asked a question about solid state batteries. There are a whole interesting range of batteries. What we're thinking here, I think, is good enough's battery, where it uses the Lisicon-Massicon glasses to make a solid state lithium sodium ion battery. Those glasses are quite difficult to make, but very interesting. Most of the so-called solid-state batteries are in fact what are called pseudo-solid-state. So what they do is take the electrolyte and somehow gel it. So popular gelling agents are things like gelatin, agar-agar, silicon fumed silica. They act as pretty good gelling agents to form pseudo-batteries, pseudo-solid-state batteries. They work quite well. They do solve a lot of issues concerning electrolyte leakage. So if you've got a problem with electrolyte going everywhere, the pseudo-solid-state battery will help do that. Like everything, there is a cost to pay. So the ion mobility is slightly lower. The electrolyte gelling agent, depending on what you use, can have an effect on the overall system, and it's usually a negative effect. So pseudo-solid-state batteries are well worth an investigation, certainly. particularly if you're plagued with electrolyte leakage and you want to cure that leakage problem. It's a good way of dealing with them. True solid-state batteries, things like Goodenoug's glasses, they're quite difficult to make, and you'd need a pretty good lab to be able to make those and to use them. So somebody's asked about using marine polyurethane for the binder. Nothing wrong with using marine polyurethane. Never tried it myself. Worth a go. Remember that your binder ratio to your active material ratio should be around about 5 to 10%. Any more than that, then your chances are you're just going to be insulating your material. And if you're insulating your material, you're going to have problems getting the energy out of that material. So yeah, polyurethane, marine polyurethane would probably work. Give it a go. Let me know how it works out for you. I don't have any plans on producing primary cells, no. I have no interest in primary cells particularly. I'm most interested in rechargeable secondary cells that are environmentally friendly as far as possible to all carbon devices is the main interest I have. Primary cells are pretty much tied up with manganese, zinc cells, extraordinarily cheap, mass-produced by the tons, very difficult to compete with something like that, so I'm unlikely to enter that field. I'm more interested in rechargeable anyway. So to recap, as I've been asked to on the ingredients of the solution, it's 100 milliliters of water and 5 grams of potassium hexacyanoferrate in one solution, and 100 milliliters of water and 0.5 grams of zinc sulfate in the second solution. The hexacyanoferrate solution is stirred slowly, while the zinc sulfate solution is added dropwise. Could you make a... So somebody's asked if you could make a 1-ton single cell putting energy density over everything. Well, I imagine you could, but I have to ask the question, why? If you want to make something, you want to make it for a purpose. I have a defined purpose in my mind, and that is to compete with lead-acid batteries in the lead-acid battery market. So I don't have much of an interest in making a 1-ton cell putting energy density over everything. But if you wanted to, then I imagine you could. But I don't really know why you would want to. The filtration will get slower because the pores of the paper are beginning to clog. As they begin to clog, it filters it better, but it does filter slower. Yes. We can speed it up, obviously, with vacuum filtration.
Or centrifuge.
Centrifuge or vacuum filtration. So we've put a vacuum pump on it. Mandy, could you get me the book, the funnel, and the book the funnel, book the flask, please? Yes, then you could put a bit of vacuum on it. So somebody's asked if these particles are small enough to inkjet print. The answer would be yes. An inkjet printer nozzle is 45 microns across. The recommended particle size to put through an inkjet printer is 1/9 of that. So anything smaller than about 5 microns across is going to be inkjet printable. Yes. And they are way smaller. That's okay, I've got one here. I just need the funnel, the porcelain funnel. Okay, so the self-discharge rate of this battery is pretty low, actually. On the batteries that we make, I'm not too sure at the moment, I'd have to check the figures, but the self-discharge rate is pretty much comparable with any other battery on the market, like lead acid, for instance. So a few points of a volt over a few months, I'm not sure. So, as we were saying, the reason we've gone for straightforward filtration is it's really cheap. It does mean you have to have patience and you have to wait until it's filtered, and that can be a problem, but just have patience, it will do. If you have a bit more money to spend and you don't want to have patience, you're going to need to buy more equipment. The next equipment you would buy is something like this. This is called a Buchner funnel. It's a piece of porcelain with lots of little holes in it. Your filter paper goes straight on there. You wet it just with a bit of water, and you put it on a thing like this. And this is called the Buchner flask. And the two fit together like that, with your wet paper here. This little nozzle here goes to a vacuum pump. You turn on your vacuum pump, and the vacuum is created in this section here. The water is sucked through. Then when you add the solution to here, the water has a force pulling it through, and it'll filter very much more quickly. When we're using a gravity filter like this, yes, it's slow. If you don't want to wait for that and you want to spend the money on the Buchner equipment, then that's what it looks like. However, it is expensive. I warn you, this particular piece here is £150, and this is £90. So you're looking at about £250 to buy this stuff. When you get the vacuum pump, the minimum pump requirement is likely to be around about £90 or so. So you're looking at about £300 if you want to get vacuum filtration equipment that is one of the next basic steps from the gravity filtration that we're using. If you don't want to spend £300, then patience, obviously. Patience and lots of coffee and the odd cigarette. Sees you through. I may cheat in here. So comments on the vanadium redox battery. The vanadium redox battery, in my opinion, is an awesome battery. It's a flow battery, and like other flow batteries, for example, the zinc bromide battery and the chloral hydrate battery, I think are excellent technologies. The chloral hydrate battery was popular in the 70s when they actually ran a VW minivan on it, I believe. Vanadium redox batteries are currently undergoing exploration for energy storage. The main issue with them is that they require pumping equipment, and there's a cost and weight to that equipment, so that the break-even point of energy storage, I believe, is round about 50 kilowatt hours. So 50 kilowatt hours and above, it's a viable technology. 50 kilowatt hours and below, it becomes non-viable because the weight of the equipment and the cost of the equipment to work the redox means it's too expensive at 50 kilowatt hours or below. So it's an awesome battery, nice chemistry, love the idea of catholytes and analytes being rechargeable, makes it extensible because it's limited only by the volume of your catholyte and analyte tank, but the problem is it has to be of a certain size before it becomes valid and usable. How's your filtration going? Are you tempted to cheat yet? Okay! Okay guys, so we're going to diverge a little bit here because obviously this is going to take hours to filter, and there are only a certain amount of hours in a day you want to spend with your Saturday watching something filter. So what we're going to do is we're going to take a scoop of the material that I prepared earlier. So we're going to put these to one side now, leave them to sediment, leave them to filter. I'll probably do a follow-up with them and how they went. Like I say, I particularly like the look of these two. They're looking nice. This is, if you compare, incidentally, the non-filtered to the filtered. So there's the non-filtered, nice and cloudy. There's the filtered, still a little bit cloudy, but clearly removing particles. We'd have to filter this again, and that will get our particles out. So I'm going to diverge a little bit here. The guys who have sedimentation already should have found that theirs filtered relatively quickly, so you should have a product. And what I'm going to do is I'm going to supply the guys with a pre-made product from here's one we made earlier. So please forgive me, but we need to get through this before it becomes midnight. So I'm going to supply the guys with that. I'm going to ask them to clear this stuff away onto one bench, and I'm going to supply them with the finished material. As if by magic. So by the time you've filtered it and dried it, it'll look like that, orangey red colour. Okay, there'll be very little of it, in the same way that there's very little of that. Okay, you don't have much. So what do you think are the problems with that? In order to use this as a battery, what do you think are the problems?
Cycle time is too less.
No. Just the problems of turning it into a battery rather than the problem of the battery itself, okay?
Materials.
The material is non-conductive. It's an insulating material. So it can't get the electricity out. How are we going to solve that problem?
Adding some carbon.
Awesome! Yeah, we could add a conductive additive. Yeah. What would be a good conductive additive?
Anything. Non-metallic is ideal because that will react less.
Yeah.
And smaller size, we grab it from the smaller component.
Yeah.
So smaller in size.
Yeah. What do you think about graphite? Would that be good?
Graphite.
It'd be awesome, wouldn't it?
Yeah.
Yeah. So here is a bag of graphite labeled number 4. And that is a conductive additive that we're going to add to our material because our material is non-conductive. Now, so once you've scraped it from the filter paper, you do need to dry it a little bit. Okay? Yeah.
Has that had the number 3?
No, not yet. No. This is a speeded up result from adding 1 and 2 and filtering it.
Right.
Oh, good question.
Yeah.
All that is when you filtered it and you scrape it off your paper, that's what you'll have. You need to dry it a little bit, but that's what you will have. Once we've done that, we're going to do the next stage. So this is the result of mixing liquid 1 and 2 and filtering it. And that's the finish for that. What we need to do now is turn that into an ink. The problem with that is adding a binder so it'll glue, and adding a conductive additive so it will conduct the electricity back out. Yes, those are the 2 problems with it. To solve those 2 problems, we're going to add some graphite in bag number 4, and we're going to add some binder in pot number 3. Now remember, your binder should be a ratio of around 10% by weight. Your conductive additive is around about 10 to 20% by weight. Okay? Yeah. Yes.
Yeah, we could tear.
Yes.
Try to get another of this cap. Could we get another piece of such cap so that we can tear?
So somebody's asked if they can dry their filter paper in a cooker or a cooking sheet. Yes, you can. Particularly good if you use a fan oven, because effectively what you're doing is forced air drying. So it's quite good in a fan oven. Don't raise it above 80 degrees centigrade though. Keep it really low, so put it on your lowest setting. You don't want to cook it, you just want to dry it. And the air blowing over it will really help. The clear solution is most definitely going to be waste solution, but it is potassium sulfate. Okay, so your waste solution is potassium sulfate. Utterly harmless, nothing to worry about. If you're really worried about it, and you don't want to put potassium sulfate down, a few milliliters of potassium sulfate down your drain, you will have to dry it, collect the dry powder, double bag it, and take it down to your tip disposal to put in there. But you are being completely and utterly anal if you do that. It is potassium sulfate, pour it down the sink.
So we are going to add like 10%. I have like 50 grams here. So
No, you don't have 50 grams there.
sorry, 5 grams here.
Yeah, 5 grams.
5 grams
right.
here. So I have to go like 10% of that by weight.
Yeah. So it's always a good idea to re-watch stuff. Although we're going through this, we're asking questions as we go, we're doing the thing together. It wouldn't hurt to re-watch the video, certainly. So later on, the link, it will be available to you guys. Actually, I might just make it a public link so you don't have to keep asking, and re-watch the video, yes. If your conductive additive, we've given you graphite, you could use carbon black if the carbon black is conductive. So for instance, Ketchum, K600 is a conductive carbon black. You could add that as much as you could add graphite. So graphene would be better than graphite because it's more of a wraparound, more surface area, less volume you'd have to add, but it would add expense. Graphite's much cheaper, but you could use graphene if you wanted to. You couldn't use copper-2 oxide as a conductive additive because what will actually happen is you'll form a copper hexacyanoferrate. So somebody's asked how good is the conductivity of the hexacyanoferrate, and I think we've pretty much covered that. It's not very conductive. You need to add 20% conductive additive as a minimum. How many inches of mercury do you want your vacuum? I have no idea. Normally, an Edwards C somewhere about 4 litres per cubic feet per minute is going to pull off enough of a vacuum. Could you use it for electrolysis to make graphene from graphite? I'm not quite sure how you would do that, guys. So we're using a hexacyanoferrate, and we're adding a bit of graphite to it, and we're making a cell. So I'm not quite sure what you mean. If you could expand on that question a bit, that'd be great. My initial reaction is no, but I don't really grasp what it is that you're asking. So just to run through that binder percentage again, because people are worried about the binder percentage. The percentage of binder is round about 10% of the weight of other materials. The percentage of conductive additive is round about 20%. So, for example, if we take 5 grams of our active material, we need to add about a gram of carbon, a conductive carbon to it, making 6 grams in total. So we need about 3 grams of binder to it. So again, 10% binder, 20% conductive additive, and the balance being your active material, the 70% being your active material. So just to run that through again. And then to repeat, somebody asked about carbon black. If the carbon black is conductive, for example, K600, it's not better than graphite, but it will do just as well as graphite. So in mixing this stuff, you can either just use your spatula, your wooden spatula, and just stir it around on top of the glass plate, and you will mix it up. Obviously, not particularly well, but you will mix it up. Another option you've got, if you happen to have one, is this wonderful piece of kitchen equipment. Fantastic stuff. A mortar and pestle. Chuck your materials in there and give it a good going round with a mortar and pestle. The density of that is 1.011, roughly 1 gram per milliliter. So 3 grams is going to be 3 milliliters. So use your pipette and pipette off. So Ian, there aren't any silly questions, mate. You're quite right to ask. Okay, absolutely 100% right. This is information other people need, and they're good questions. Okay, so about 3 milliliters of that is what you need. You have about 10 milliliters, so plenty. Those pipettes are in half milliliter graduations. It is right there.
Now we can give the material then.
Percentage again on the potassium?
Percentage again on the potassium.
Yeah.
So somebody asked about the percentage again on the potassium. I'm sorry, I don't really understand that. Could you repeat that question, maybe expand a little bit? What's the problem?
No, since I have less, 0.5 gram.
Uh-huh.
Yeah, 0.5 grams. So we
Half a gram.
half a gram of this material.
Yeah.
So I have to be like 0.5 ml.
That's, yeah, 20%.
So you've got, this is half a gram?
Yeah, half a gram.
Yeah, so that's 0.5 of a gram.
Yeah,
So you need 20%
20%.
of carbon. So that's going to be how much? 0.1 of a gram of carbon, giving you 0.6 in total. 1%, 10% of that is 0.06.
Yeah, 0.5 ml.
0.0.
0.0, yeah, 0.05.
So not half a milliliter,
So
a 20th of a milliliter.
then how do I, because if I feel that it's a big lump.
Thank
then
you,
maybe I
Lee.
need to add some additive like water to paste it.
You'll find that's quite damp enough.
Oh, okay. So now, what is the size of a drop?
A drop is 15 microliters.
15 microliters. Now,
And you want 60 microliters,
yeah,
so 4 drops.
Yeah.
Now it does make sense.
Okay, 4 drops.
Easy, easy. Yes, one.
1.
Okay, so it's 1:1 potassium hexacyanoferrate by weight to zinc sulfate. So when you make your two solutions up, it's 100 milliliters of water and half a gram of potassium hexacyanoferrate. Then it's 100 milliliters of water and half a gram of zinc sulfate. So it's a 1:1 ratio by weight. You need to have the carbon as well.
Carbon.
You've got half a gram of that, so 0.1 gram of carbon.
Even smaller quantity.
Well, you just added 60 microliters, so...
Yeah, that was good because of the pipette. So now we need a piece of paper here.
Tiny piece of paper.
Yeah. So cheers. Cheers.
It's getting very exciting because you're actually getting quite near to making the device here. So there is some argument that I should just do this. That's wrong. Here, what we're looking at is the trouble you have when you just do it for the first time. You go through all of these problems for the first time. It's difficult to make these things. You think when you watch me how it's easy to make them, but it isn't. It's quite difficult to make them and requires a considerable amount of skill. You need to learn that skill if you want to make batteries. There's no better way of learning that skill than making that battery.
What is the quantity? 0.1. 0.1 grams. 0.1 grams. You see? No, it's not even responding to that. Anyway, we have 2 decimal points. That's 0.01 gram or 0.1? 0.1.
Yeah.
Yeah. 0.1. So we have to decrease. This is 0.15. We have to be very careful.
Yeah.
So let me just check with you guys what it is you're doing. Tell me what you're doing.
Adding
carbon, and the binding material to the material. Half an hour.
Yeah. Heard it 100 times.
Hexacyanoferrate. That one.
Just so quickly.
Say it in Klingon.
Exactly. I know.
And then what? What are you doing then? After you've done that? Mix it together?
Yeah.
Then what will you do with it?
Paint it on.
Absolutely, paint it onto the graphite. Absolutely. So that's what you're doing. You're mixing those three components. Then you will paint it or smear it on with your spatula onto your graphite. Yeah. So somebody's asked if it's okay to use other sulfates, like for example magnesium sulfate. The answer is yes. You'll get a magnesium hexacyanoferrate. Use nickel sulfate, you'll get a nickel hexacyanoferrate. If you use copper sulfate, you'll get a copper hexacyanoferrate. As long as the hexacyanoferrate is insoluble as a resultant product of the potassium hexacyanoferrate mixed with the sulfate, then you will get a result you can use.
So 0.1 gram of graphite.
Awesome. Chuck it in there and grind it up.
And we have 4 drops of bond
You do.
and 0.5 gram of
Cyanoferrate.
Cyanide.
It will be very soft. It won't take long. Actually, you could just use a palette knife on this, you know.
Right.
Once you weigh it out, just put it on the glass and just mix it up with a palette knife.
Yeah.
Be fine. Equally. Yep. In fact, I'd like a demonstration of that actually, just because people, if somebody doesn't have a mortar and pestle, I'd like it to be demonstrated on the glass. That'd be awesome. Yeah, if you wouldn't mind weighing it, it'd be great. Yeah.
No, just
Can I borrow your spoon? That's good, right?
So I'm just going to. That's really why I was checking you knew what you were doing.
Yeah.
I need 4 minutes.
We're good for
Awesome. 4 minutes at least.
exactly 4 minutes. Yeah. So I've got
If you could do a little singing or dancing, that would be awesome.
0.7. So what do we think? How much? By the way, it was 4 drops and it's 0.5. Yeah. So I need about 6.
over 6.
I'm gonna go with 6.
This paste is not dressed. It looks good. It looks very good. So we have done 1 drop first. 6 little drops.
Right now. So I'm going to do that separately. So it now weighs nearly 1 gram. It's quite heavy, isn't it? Yeah. Perfect. So 10% would be 0.1. No. 10, yeah.
So now we have done.
I think it's a fair amount.
Is it?
Did you take that in the same quantity, like 0.5 gram?
Very close.
Yeah, 0.6.
Weighs nothing. Yeah. There's a lot there.
Weighs nothing.
It's still nothing. Still nothing. How about now? Still nothing. You think this is not working? Possibly. Maybe it's too small.
So that's 0.2 without it on. And it's 0, so that's twice as much.
Get another bit of paper now. Take away from that. See, that doesn't work.
Not quite.
It doesn't change when I do it.
No. Yeah. Drop from 2.8, so 0.25 minus 0.5. So
it's gone down. I'm going to go with that.
I think that's perfect.
I don't really need that spoon.
So you're mixing it with.
Yeah.
So it might be not scratch.
So somebody's asked what the resistivity of the coated electrode should be. It will be pretty conductive, in the order of sort of 1 ohm per square, somewhere around about there. But it will work whatever the resistivity to a degree. The likelihood is that the resistance that you're going to hit in your device is going to be more significant on the crocodile clip than it is on the resistivity of the electrode itself. Yes, the irony, low battery. So if you have a look at Fergus's mix there on the bench, is that kind of nice brownish colour mix? That's what we're looking for, and we need to put that onto our current collector. So that is our graphol current collector. And cover about a square. So they're just about a 1.5 centimetres. So go 1.5 centimetres up on each one and cover that square. Now Fergus has picked himself up a palette knife, but you can do this with your wooden spatula just as well as you can with the palette knife. So just smear it on there, it's a nice thin paste. There we go, and we leave that to dry. That is the cathode finished. So Fergus has finished one cathode. Now what we're going to do with this link, remember, because we are going, we're trying to get through quickly because I understand the time is a long time. It's Saturday evening and really thank you very much for giving up your time to watch this. But we are going to leave the link up. So I would recommend that you watch through the link again, and you should have materials left in your kit to try again, about 3 or 4 times I would estimate. So watch through the link again and try again watching through the link. So the link will be available so that you can watch it again and try again with your kit. And if anybody wants to buy the kit so they can try, then the link again will be up so that you can run it through with the kit and make these devices. And there we go. Fergus has got 2 nice cathodes made and he's going to set them to one side and we'll dry those cathodes because they're looking particularly beautiful. In fact, both Ian and Matt are looking enviously at them. But they're beautiful. So put them to one side and we'll dry those in a minute when Ian and Matt are finished. We'll pull forward a dryer.
Yeah, just of
What's that? The graphol ones.
These
Yes,
ones,
it is the graphol ones that you want.
And square on each side, yeah?
Yeah. So just to recap for folks, because I've asked a recap of this, you take the zinc sulfate and measure out 0.5 gram and add that to 100 millilitres of water. That's bag 2. Bag 1 contains the potassium hexacyanoferrate. You measure out 0.5 gram of that and add it to 100 millilitres of water. Stir the solution of potassium hexacyanoferrate and add the zinc sulfate dropwise until you form an orange precipitate. Separate the orange precipitate either by filtration, vacuum filtration, centrifugation, or just leave it to one side and let it drop to the bottom of the glass. That is your zinc hexacyanoferrate, and that is the active material. Once you've collected that material from the filtration or separation, you mix it with conductive additive, graphite, as a good conductive additive, and binder, which you've been provided for in tub 3 and bag 4. You need 10% of binder, 20% of conductive additive, and 70% by weight of the zinc hexacyanoferrate. Mix it and then paint it onto or smear it onto your graphoil, and that will form your cathode. And we can see here that all 3 of the guys have made their cathodes. Well, actually we're just waiting for one more, and you only need to smear it on one side.
Yeah, and the zinc is slightly a bit white.
Yeah, it doesn't matter. Yeah, it is. We don't need to add water, but if you add water, it doesn't matter. If you add water because it's getting a bit dry and whatever you're mixing it with, it doesn't matter. It won't affect anything, and we are going to dry it in a moment. So adding water will have no effect whatsoever. So if you want to dry something, and the stuff's still a bit wet and you're looking to dry it, the easiest way to dry it is just under a hairdryer. We're going to dry the cathodes now under a hairdryer. If you've managed to filter off your zinc hexacyanoferrate and you're wanting to dry that, then you can dry it under a hairdryer as well. So scrape it off your filter paper, put it onto a plastic cap or a piece of something that's plastic, pop it under the hairdryer, and give it about 5 or 10 minutes, it will dry. Then you can mix it onto your cathode, dry it under the hairdryer again. What we're going to do now is clean everything up, get the hairdryer ready, and then dry those electrodes that we've just made. So we're going to clean everything away and get the hairdryer ready. If you add zinc, so another question, if you add zinc hexacyanoferrate to what looks like, is that cobalt oxide? Oh, okay, right, okay, so if I add zinc hexacyanoferrate and go and put it in the kiln, do I get graphene doped? Okay. Well, that's a really interesting experiment, actually. So what has been asked here is if we mix zinc hexacyanoferrate with graphene oxide and reduce the graphene oxide thermally with heat, will I get a doped graphene oxide? Well, the answer is probably not. What you'll get is an intimate mix of graphene and zinc hexacyanoferrate, but you won't directly dope it. What might be a better approach is to mix the graphene oxide with the potassium hexacyanoferrate, then add the zinc sulfate to that, then filter and dry. There's a high likelihood that you would get a doped graphene then. I don't know for 100%, but it's an excellent experiment to try. So somebody's asked about the effect of varying the thickness. Now, this is a thin film battery, so it will be power dense because there's not much distance for the electrons to travel. So give me 1 second while I answer this question. The thicker I make it, the higher the resistivity, higher the resistance, because resistivity is a property of the material. The thicker, the higher the resistance, the less power, but the more energy. So a thicker material will give you a more energy dense, but less power dense device. So what we're going to do now is dry those, and all we're going to do is put it under this hairdryer. So you've got a hairdryer on a stand, we just turn it on, let it blow a little hot air over there, and that will dry it. Okay. 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 Thank you for the suggestion. Help me!
It's blowing away.
Obviously, we need some kind of way from that. Right? I'm looking for something. That'll do nicely. I hope you remember whose is whose. Because there is a prize.
Yeah.
There you go. Yes, it is. It's very thin, so it's going to dry quickly. It's the same thing with the when you've collected the zinc hexacyanoferrate, you've collected it and you're drying it, it'll dry in a minute or two. So I do appreciate that we didn't finish the filtration and we speeded it up a little bit. But then it is coming up to 7 o'clock. So people do have other places to be. I want us to get to a point at which we've followed it through. We will leave the video up as a live link, so you can watch the video again. Okay, there won't be the opportunity to ask questions, and that is unfortunate, but you will be able to follow through again. And we just want to make sure that we don't take up too much of people's time, because this time has been donated, and I'm very grateful for the donation of the time, and I don't want to take advantage of that time donated. I think that's probably dry enough, don't you? Yep. So it really doesn't take long. And there we go. So we've got a nice cathode plate there. So there is our graphite here, and there is our zinc hexacyanoferrate active material applied onto the end of the plate there. And that is going to actually be our battery. So all we do now, this is the cathode component. We need a separator. And the separator is, remember, this material here. That's our separator. And we need the anode, which is the piece of zinc, which is this shiny metallic material that's in the kit there. So those are the three main components. There is only one other component we need, and that is the electrolyte. Now we're going to use zinc sulfate as the electrolyte, and that's in pack 2. Now we need very, very little electrolyte. So the molecular weight of this stuff is 161.47 grams per mole. We need a 1 molar solution. 1 molar solution is where I would put 161 grams of this into a litre. I don't have 161 grams. I want about half a gram. So if I take half a gram of this and add it to 3 milliliters of water, which is not very much, wait for it to dissolve, that will be a 1 molar zinc sulfate solution. And that's going to be our electrolyte. Now our batteries are very small, so we're likely to need about 1 milliliter of electrolyte to finish making our battery on the fourth component. So we need to make the fourth component. So to recap, we have 4 components. We have the cathode, which is covered by zinc hexacyanoferrate, and that's the graphite cathode with the zinc hexacyanoferrate, component 1. We need an anode, and our anode is a zinc ion battery, so we're using a bit of zinc, component 2. A separator, which is this here, our separator plastic, component 3. And our final component is our electrolyte, and for that we're going to make a 1 molar solution of zinc sulfate. To make 1 molar of the amount that we want 3 milliliters of water and half a gram of zinc sulfate. And that's what the guys are going to do now, and I'm going to have a look at some more of your questions and answer your questions while they're doing that. So half a gram of zinc sulfate, 3 milliliters of water. Deionized water is preferable. Good idea. So somebody got that a little wrong. The zinc hexacyanoferrate coated graphite is the cathode. The active material on the cathode is the zinc hexacyanoferrate. We have to put it on a current collector, which is graphite. So the graphite with the zinc hexacyanoferrate coating is the cathode. The anode is the zinc metal. So water, as you know, will freeze at 0. With a little bit of salt added to it, you will depress the freezing point, but it will freeze round about -5, -10. If you want to get the freezing point even lower than that, you have to add an antifreeze. Polyethylene glycol 200 at about 3% would be an effective antifreeze to depress the freezing temperature to around about -30, -40. So the separator that we've given you is actually a CellGuard product. It's a polyethylene, polypropylene, polyethylene tri-layer where the outer layer is coated with zirconium oxide. It's quite a complicated material. What the zirconium oxide does is prevent zinc ion migration. So it holds the zinc ions in the catholyte side more successfully than tissue paper would. So tissue paper will form a separator in so much as it's ionically conductive and it keeps the 2 plates apart. The CellGuard product is superior to that, which is why it's been provided, and will give you a longer cycle life because it prevents zinc ion migration. If you want to get some tissue paper and paint it with a zirconium oxide paint on the anode side, you would have pretty much the same effect. So somebody's asked if we can reduce the kits in price to include only the exotic ingredients. You have to remember that the kit price doesn't include the exotic materials. It also includes the time I'm spending with you to walk through those kits. So the kit is the materials that you find difficult to get and the time I'm putting in to teach you how to use the kit. So somebody's asked if we'll be spending time covering how to make fulminating mercury. Well, the answer is no. So I suspect that's a joke or a witty comment or something like that, but it really isn't anything we actually do. We don't work with explosives, so we wouldn't be showing how to make fulminating mercury, no.
It's half a gram, isn't it?
It is, mate. Half a gram of zinc sulfate to 3 milliliters of water. Yes.
chilled out in manufacturing.
Sorry?
Yeah,
So we're going into mass production.
Awesome! Manufacturing in on the line, working on the line. So you're working for the man on the line, eh? Okay, so some people are having problems with their electrolyte evaporating. Actually, the chances are it's not evaporating. The chances are you're charging it at too high a voltage, so what you're getting is electrolysis of the water. What you might try to do is to reduce the voltage that you charge it at, so you're not electrolyzing. The electrolysis process may be so slow that you're not actually registering it by off-gassing, but it's still electrolytically splitting the water and apparently drying. Yeah, fantastic. Whatever it takes to get it dissolved. Me, I usually stick my finger in.
It's almost. It's almost.
Like I say, it doesn't take long. You have very little material. It's the fourth component for the. You do realise I was joking, because God knows what contaminants on the edge of that finger. That'll be it. Yeah. Yeah.
Fell for it.
The best one. Is that right?
All of them will work. Yeah, will work.
Which one?
Oh,
I think we've got one of each.
Okay.
Okay, no, that's all right though. It's okay.
Which one do you think's yours? Mine were the rubbish ones. Why don't you use that one? That's good.
Yeah, that's good. Good formation.
Oh, let us.
Where is he? That's okay.
Yeah.
That's 9 volts, so no. 2 seems to be awesome. Thank you, man.
We've got that 4 bits.
You have your 4 components ready to go. Awesome. Okay, well now we're ready to put a battery together. Now we've got those 4 bits all ready. So, all we do to put the battery together, obviously, is we clean our workspace so that we've got space. Awesome! So all this stuff, let's get it out of the way and let's make sure we've got everything lined up and we're ready. You should have your pipette ready somewhere. You may have wondered why we added the zinc sulfate to the potassium hexacyanoferrate. It's at this stage it becomes relevant. We haven't put any potassium hexacyanoferrate onto the pipette. The pipette's only been in water or zinc sulfate. So when we put the zinc sulfate electrolyte onto our battery, we don't have any electrolyte contamination. We kept them nice and separate, nice and clean. All we're doing is putting zinc sulfate on there. So it just stops a little bit of cross-contamination if we add that one to the potassium hexacyanoferrate. So let's line up our bits. We've got that, we've got those, we've got separator, we've got that, our pipette, awesome, that, everything else is cleaned away. Just move those out of the way so we don't need them. So there are the components of your battery. It's really easy to do the next little bit. The next little bit is cathode. A little bit of this off. Separator. 0.5 milliliter or so of your electrolyte. That is your battery. That's all there is to it.
all we're going to be doing now is charge and discharge that device. So it's a really simple device. It's in the open air. Now, that's not a good thing. It's always better that you give it some protection. But this device will still work, even though it's in the open air. It's a very robust device. It's very powerful, very robust. And even doing it in the open air, we will still get this device to actually work, which is cool. In order to charge it, we have our charging cables here. Personally, I hate these cables. I hate them because of the trouble of doing that. They invariably slip in my fingers, and I have a nightmare just doing that. So, I don't like them for that. But these will move if all we do is leave them like that. We need to do something to stop them moving a little bit. And the easiest thing to do is just put a bit of plastic of some description on there, and then a light weight. I use this little bit of plastic here. Just means that I can just pop that down there, and I can put something on there as a weight, and it just means that everything stays in place. It's not doing anything, it's just stopping things moving, because it is a pain in the neck when these things move. But what I'm looking for now is a little weight to put on that, or some description on it. There is a jar of something that weighs an absolute ton. It's weird stuff, and it weighs a ton. It's kind of like a liquid metal. Let's see it. Oh, this is surprising. Can I feel that? So this is a salt. It's actually what's called a wise electrolyte. So this is what's called a wise electrolyte. It's a very, very concentrated salt solution. It's so concentrated that it's surprisingly heavy. It actually weighs a lot. So there's about 150 milliliters in that. You'd expect it to weigh about 150 grams. It doesn't. It weighs about half a kilo. So it's a really concentrated salt solution. And it makes an excellent weight for holding those things together. But the only use I can think of for it. But it works really well. So just make sure that those things stay together. Obviously, our graphole, remember, is our positive. So let's connect the positive to that. And you can see it slipping. That's why I told you I hated them. Connect the positive to there. And the negative to here. Now, normally when we charge these things, we use meters. We use meters so that we can register what kind of charge is going on here. When we put it on the voltage, the ampage will draw, and we'll see an amp reading on the meter, and that amp reading will fall. As the amp reading falls to 0, it means that the cell is charging to the voltage that we're applying. Now, the spirit of this is to do it in your kitchen with the least amount of material. So we're not going to charge this one using our power meter. The guys will put it onto the actual meter and you can see the meter readings. I just want you to show you with this one an alternative way of doing it so you can get a result out of it, but you won't necessarily know what the numbers are. Then we'll repeat that result using our benchtop's power supply, but you don't need a benchtop power supply, and with a multimeter, but you don't need a multimeter. Or you can use any combination of those things to give you an idea of what your device is actually doing. Here, all we're doing is showing that the device will work to some degree. That's all we're going to do. And we'll do it a bit more accurately, or the guys will do it a bit more accurately, by connecting it up to the multimeter and the benchtop power supply. What we're going to do is charge it from a battery and try to spin a motor from a DC charge. And we have a little motor here. This motor is meant for us to test our device here. So I open up my motor. Got a propeller on it so that we can see the propeller spin. And we need to strip off a little bit of that end material there. I'm going to use this, but you don't have to. Oh, no, maybe I won't. Maybe I'll use something else. I'm not too sure. Yes, I'm going to use a trimming knife blade, actually.
some way of stripping that insulation off. You have a stripper, awesome. If you have bravery and a trimming knife blade, awesome. If you don't have either, I suppose you could always use your teeth. Just some way of getting that material off there so that we have a bit of exposed wire that we can connect easily to. So I'm just cleaning that off to expose the wire. And there we go. With a bit of exposed wire there. Very difficult to see, but it is there. Actually, I already have a little bit there, so let's just clean that off. And then we can connect our cell up. Now the way to charge it with the battery is, this actually device is about 1.8 volts. I'm going to overcharge it a bit by using two C cells connected in series. You might see what I've done there. I've taken a magnet, neomagnet. If you pop the neomagnets on, it makes it a bit easier to charge them, because all you then have to do is check which way around it is. So you see, that's the positive. Attach the positive, just attach itself, attach the negative, and we'll give that a little bit of time to charge. It means I don't have to hold everything on. The thing will just charge all by itself.
Gideon suggests the clothes peg.
Good suggestion, Gideon. Clothes peg would work nicely. I quite like that as an idea. I also like this. I actually really prefer the benchtop power supply. I'm trying to do something where if you don't have a benchtop power supply, you've got another way of trying to charge it. Me, I like benchtop power supplies. Let's see if that's actually works, shall we? Quite excited actually, because I haven't got a clue if it's going to work or not. I'm hoping it does. If it doesn't, we're going to stick 20 volts on the benchtop for it and see what happens. There's him. I can get it connected. I'm having trouble connecting. Okay, that one's on. Yay! We actually got it to turn! That's ridiculous. We actually got that to turn. Well, it's short-lived, but it turned. Let's try it again. Yeah. Let's see if we can make a better connection, because I have to say, I didn't have much hope there. Well, you had faith. Yeah, let's see if we can get this a better connection as well. You guys worried about time?
No. I've taken all of my stuff. I thought it shouldn't be too bad.
No, this bit's not scary at all.
Yeah. It's quite hard to see.
It is hard to see. Yeah.
No, I haven't. I was trying.
Oh, that's a clear wire there. See if I can get a bit clearer here. Doesn't have any short circuit. Oh. That's okay. I think I've got it. Okay, let's try it. Very exciting. There it is. There you go.
It's still thin.
It's to do with the, yeah, the connection's really poor.
No, you got to strip a bit longer. It's like 2 millimeters or something.
It is. It is. It's not.
We're not really able to hold it.
It's not that. It's
It's the connection is not very good, because I'm not making a good connection.
Yeah.
They're quite delicate, hey, and I don't want to pull the whatchamacallit off, because they're quite delicate.
Ah, you see?
Oh yeah.
Lots of jobs.
You've got a lot of wire showing now. Fair amount. No, let's try a fair amount then.
Yeah.
Oh, that is a fair amount. Look at that. That's a ton of it.
Do I charge it?
Yeah, charge it in. Yeah. That's a huge amount, man. Well done.
That's my electrician.
Oh no, I'm mostly proof it actually works, to be honest.
Yeah.
I tell you what, it is always a fear when you do things like this because you never know if it's going to work. This is our first ever live event, obviously, and obviously we've all been quite nervous, to be honest, because we didn't know if it would work or not. So it's pretty awesome that it has in fact worked. Let's try it. I know we shouldn't, but I'm just too keen. There we go. Oh, back of the net. Okay, guys, there you go. Our battery made really badly. Spinning a motor. No, sorry, my mistake. Our battery made beautifully. Spinning a motor. What we're going to do now, just to round up, is obviously the seminar is basically finished because we've led you right the way through. I've got a few more questions I'm going to answer. As I answer those questions, the guys are going to connect up. We'll rearrange the camera a bit so you can see the actual power supply. We're going to connect up the device to the power supply and to the motor, not the load. We'll connect to the motor so we can get some actual numbers out of this. And we're going to round up by doing those actual numbers out of it and answering the last few questions. Okay, guys, would you like to do that?
Yeah,
Connect to the power supply. I'll answer these questions and we'll finish up.
We're going to do the same batch.
Same batch, or we can create a new batch, no problem.
You do the same batch here?
Yeah. This looks better.
Okay, so we had a question here about a lithium-ion prismatic cell. So a prismatic cell is where it's layers. And they kept it short-circuited for some time, and it stopped working. Was it caused by dendrites? Probably not. Lithium-ion batteries work by intercalation of the lithium ion into the graphite. If you deintercalate all of the lithium, the graphite galleries collapse and it becomes non-rechargeable. It's very difficult to buy zinc hexacyanoferrate nanoparticles. You can buy them, but they're stupidly expensive. So you could do that. You could make a battery that way. It'll cost you a small fortune. It's better, I think, to make them yourself because it'll be very much cheaper, and you can mass produce them. You can make many of them. So the graphite eventually showing signs of oxidation was a really interesting question. The graphite doesn't oxidize so much at that voltage because it's very low. Over sort of about 3.5 to 4 volts, you'll see the graphite, showing signs of oxidation, pitting, and degradation. But it is a lamellae structure, and in an aqueous solution, it will delaminate. So what happens is it puffs up and it becomes very porous and quite fragile, quite friable. You wouldn't really want to use graphite in a full battery production because of its fragility. But this will work just as well on stainless steel mesh. So you could use stainless steel mesh if you wanted. We sent you graphite because it's relatively chemically inert, and that's always a good thing when it's relatively chemically inert. But stainless steel 316, 400 mesh will work just as well. Suggestions for the enclosure for a battery? Well, the enclosure would work quite nice in just a polypropylene pouch cell. So you stick it in some polypropylene, put it in a vacuum sealer, and that would make a nice enclosure for it. we will be giving a view of the discharge curve. Initially, we're going to spin a motor, but we will put it onto the BK precision load so that you can see what the discharge curve actually looks like as well. Why no active material on the zinc plate? It's a zinc ion insertion battery. So the zinc, in this case, is the active material. We're using the zinc ions from the zinc sulfate electrolyte to insert into the hexacyanoferrate matrix. But any other zinc required, then it comes from the zinc plate, which is a source of zinc ions. It's a zinc ion sink. Now, obviously, that zinc plate, for the amount of zinc donating, is really, really thick. That zinc plate could be much thinner, but it is the source of zinc ions for the battery. Okay, so most people think that above 1.23 volts, then water will dissociate into hydrogen and oxygen. And that's very true. It will do under certain conditions. And that is the normal conditions that the electrode potentials are measured at. Now, it doesn't hold true for lots of other conditions. So, for example, with a carbon electrode, oxygen evolution reaction is inhibited. So you can actually raise it to a higher voltage. Inhibition also occurs when the electrolyte is relatively concentrated. So 1 or 2 molar zinc sulfate is enough concentration of a neutral salt to inhibit electrolyzation of water. Another good option, as somebody said, can woven carbon fiber cloth work instead of graph oil? The answer is yes, yes it can. It's like stainless steel mesh, it will work just as well. So somebody's asked, why not sell zinc hexacyanoferrate nanoparticles on eBay to help fund our experiments? We're very interested in people experimenting. We don't really want to spend a lot of time producing zinc hexacyanoferrate. We really want to spend a lot of time producing our batteries. So we're quite happy to do courses, to do suggestions, to do kits and all that kind of stuff. But we wouldn't produce a lot of this stuff, and a lot of it wouldn't be sold. So it's not really a thing that we would want to get into, because we don't think it's something that we'll be able to make. We don't think it's something we would be able to make a successful contribution to the fund with. So a DIY capacitance meter. So have you ever considered of making a DIY capacitance meter for measuring large farad capacitors? Not really. Once you start doing things like that, you come into a whole host of other problems. Like if we make DIY meters, making a DIY, considered making a DIY capacitance meter. Okay. So we actually use something called a Sencor LC meter, which will measure up to 20 farads. We use that, so we actually have a meter for doing that. Doing it yourself for measuring capacitance, you just use a known resistance and measure the time and use that to calculate what your capacitance would actually be. So it's not that difficult to do. I did a video on it actually, if you want to have a look at that. So I've got a question here saying the electrolyte of my zinc vanadium pentoxide turned black. We're not actually using zinc vanadium pentoxide here, but if you use zinc vanadium pentoxide as a zinc and cyan battery and your zinc has turned black, then that is passivation of the zinc surface. And so you're getting oxide formation and passivation for your vanadium pentoxide battery. What's the difference between the anode and the cathode of an all-carbon battery? One's plus and one's minus. And there is no other difference. Why didn't you make an all-carbon supercapacitor in this session? Well, we've done lots and lots of all-carbon supercapacitors. The problem here is the techniques of making batteries. That's been the big problem, is that people haven't felt capable of going out and making a battery. So it doesn't matter if we make a battery or make a capacitor. The skill set is still the same. You still make the ink, you apply the ink, you dry it, you're some way of charging it, some way of discharging it. So it's the same set of skills required, whether it's a capacitor or a battery. There's nothing wrong with letting it filter your zinc hexacyanoferrate. If you just leave it there and it dries completely, there's nothing wrong with that. Just wet it and reuse it when you mix it up. It's going to be fine. So somebody else mentioning here stopping short of off-gassing at 1.2 volts. You've got to remember that the off-gassing reaction of water is being measured against a standard hydrogen electrode potential under standard conditions. That's not the same environment you will find in a battery. If you use a different salts or a concentrated salt solution, then you can raise the overpotential of water much higher. So just using a 2 molar zinc sulfate solution will allow you to charge a battery at somewhere between 1.6 and 1.8 volts without off-gassing. If you use a wise electrolyte, something like a 17 molar potassium acetate solution, you can raise that voltage to something like 3.7 volts without off-gassing. So the standard answer, water electrolyzes at 1.23 volts, that's very true, but only true under standard conditions. It's not true for the conditions you find in an electrochemical cell. You can change those conditions. Somebody's asked just to cross-check, it is the graphite that gets painted with the zinc hexacyanoferrate. The zinc is the anode and it gets covered with nothing. So the zinc gets connected to the negative. The hexacyanoferrate is painted on the graphite and that gets connected to the positive. So when we connected it up to our 2 C cells in series, we've got no idea of how much we're putting in. When we connect it to a motor, we've got no idea how much we're taking out. We're only doing that to a baseline version to show you that the battery works. If you've made that battery and you don't have the meters, it's still going to work. And that's the only reason we did it. What we're involved in now is putting it on some calibrated equipment that most people just don't have. So we have the calibrated equipment, so we're just putting it on that equipment now so that we can have a look at the charge and discharge. But by putting it onto a couple of batteries and running a motor, we have no idea what the capacity or load capability of that battery is. All we really know from that is it works, and it works quite well for a small device. Is this zinc battery better than our old carbon battery? No. It's a good battery, but it's not better than ours. It's actually a zinc ion insertion battery, remember, not a potassium ion insertion battery. We've removed the potassium and replaced the potassium with zinc, making it a zinc ion insertion battery, not a potassium ion insertion battery. So if you scaled this up and you took the voltage above the 1.8 volts that actually should charge at, it will off-gas. It won't recombine, it will off-gas and it will dry. That's not a problem if you hold it lower than 1.8 volts, or if you have some strategy for the off-gassing. Remember, lead acid off-gasses, quite a lot actually, and off-gasses hydrogen. What you need to do is make a flooded cell, top it up with water every now and then, if that's what you want to do. If you don't want to do that, keep the voltage at 1.8 volts or lower. So in order to make the enclosure, one really interesting idea was maybe fold over a bit of packing tape. Somebody suggested that, and yeah, that would work quite nicely actually. What would work quite nicely if you don't want to use packing tape is Kapton tape, polyamide tape. That would work quite nicely as well. So it is a zinc stripping battery. You need the zinc anode. If you use some other material, for instance, you wanted to use graphite or carbon fiber or stainless steel as the anode, you would first of all have to plate it with zinc. You don't need a massive plating of zinc, but you would have to zinc plate it because it is a zinc ion insertion battery. So all batteries pretty much are covered by Peukert's law. If you charge them and discharge them at very high C rates, you will damage the battery, you will push the redox reaction too far, and you will get less power out of it. All of them react like that, including this one. If I were to charge this consistently at 10 volts or so, I'll destroy the battery, yes. If I were to try to discharge it at 200 to 300 C or so consistently, I'll get very little power out of it. That is true of every single battery, including this one. Let's have a look. Is it charged?
Yeah.
Oh, right. Well, let's discharge it then. Okay. Just check that. We've got that connected to the positive. That's connected to the negative. That's connected to the negative. That's connected. It looks good. The head back of the net. So we've got this on our power supply. We've charged it at 2 volts actually, so it is a bit overcharged. Got it connected up to the positive here. What we're going to do is swap the positive off from the charge to our load. Our load is a BK precision load. We're running that through a computer. Showing the screen here, I think we'll just get a bit of a opening up there so that camera can see the screen. And so a little bit more, a little bit more, a little bit more, a little bit more, and stop, and too much, and a little bit down, and stop, and I'm joking, obviously. Andy, do me a favour and just flip that heater off, please. Thank you very much. So we have our computer control here. Very difficult to see that actually on there, so we'll probably try to talk about it more than actually try to show you it. But this is the PC control of the BK Precision. And we're going to just discharge this quickly through the Precision because it's now 7:31, so really it's time to finish, guys. And we just charge it through there to 0 volts. So let's just connect that up quickly and see what we get. Oh, we've got a nice voltage on it. So we've got it on there, and we're showing 1.92 volts there as being the charge voltage. Incidentally, you can see kind of the rate of discharge for this device. I'll click start, and we should get a, there we go, discharging 6 milliamps, and there's the voltage drop as it discharges at 6 milliamps. Bear in mind, guys, this cell is that big. So the fact that it will do anything at all is really, really impressive all by itself. So I haven't made these. The guys have made these. So this is what we can get by making it for the very first time. So only Ian has made batteries before. The other guys here have never made them before in their lives. No, it's to do with the reflections, I'm afraid. I'm afraid you're just not going to be able to see the screen here. It is to do with the reflections. Now, your best bet is to watch the numbers ticking down here. These are the voltage readings. This is the milliamp draw. You can see that it's at 6 milliamps. You watch the timestamp, you'll see how long it takes to do that. I can tell you that it's a fairly linear curve going down. So yes, pouching the cell will help with flooding it because it's just all contained. So if you pouch it, it's going to help. So somebody else is asking again about the possibility of regenerating the collapsed material in the lithium cell. If you're a chemist, open the cell, scrape all the material off, and chemically intercalate it, then yes, you can regenerate it. But some charging method just won't do it. I'm afraid if it collapses, it's done for. It's to throw it away. It's a waste. There's nothing you can do with it, unless you're a chemist. Then you can scrape it off and intercalate it. Guys, this is awesome work. So it's been running at 1 minute 49 seconds, and the draw is 6 milliamps. As you can see, we're at 0.82 of a volt. We're actually getting a kind of tailing off like that, giving us a sort of capacitive look. Actually, it has 2 redox potentials. There's a higher redox potential that doesn't last very long. It drops off to the lower one, about 0.8 volts. There's another redox potential. And so it'll last at 0.8 volts for a while, the second window, and then it will tail off again. So it's actually a double redox is what's happening in that particular device. It's not a capacitor. Okay. Thank you very much. Okay. Okay, guys, so thank you very much to the guys for walking through this with us and helping out and going through the battery construction. It's a pleasure to have you. I hope you enjoyed it, because it has taken a large part of this Saturday night. I know you have a party to go to. I don't, I'm sad and lonely. These guys are young and they need to go. The video will stay there, so you can follow it through again. We've been asked, so we will keep the kits up on the shop, so you can get the kits if you want. Please do feel free to ask further questions. I will try to answer the questions in good time. This is the first time we've done a live event. We'll wait for the feedback. Hopefully you enjoyed it too and found it useful. If you did, we'll hold another live event. And again, thank you very much for your time. I hope it was useful to you, and thank you very much for watching. Thank you, guys. God bless. Thank you. God bless. Cool.
Click stop streaming on the other bit.